Somewhere in the room where you are sitting right now, there is a number. You could find it in seconds. A thermometer on the wall, the weather app in your pocket, the thin line of mercury in a glass tube. The room carries a temperature, and you have never once doubted that the number is simply there, a fact of the room, the same for you as for anyone who walks in. Now strip the room. Take out the furniture, the dust, the air, every last molecule of it. Pump out the light. Shield it from every signal, every stray particle, until nothing is left but the space itself, colder and emptier than anything nature has ever built. Hold a thermometer in that perfect darkness and ask the simplest question in physics. What does it read? Common sense answers immediately. Nothing is there. Nothing can be warm. The reading ought to come back 0, the coldest cold, and it ought to come back 0 for everyone, because temperature is supposed to be a property of the place, not of the person measuring it. That is the belief you have carried since school, and it is wrong. If the thermometer sits still, it reads the deep cold you expect. If the thermometer accelerates hard enough through that same perfect emptiness, it reads warm. It registers a faint bath of heat, a glow of particles arriving from nowhere in a space that contains nothing at all. Two thermometers, one identical emptiness, two different readings, and both of them are correct. Physicists call this the Unruh effect, the finding that empty space has no single temperature of its own, only a temperature relative to how you move through it. William Unruh worked out in 1976 exactly how warm the emptiness becomes for an accelerating observer, and the answer has been sitting inside our best theory of nature ever since, unmeasured, argued over, and quietly refusing to go away. Because if the vacuum can run warm for one observer and cold for another, then something you trusted your whole life, the plain reading on a thermometer, is not a fact about the world. It is a fact about your journey through it. Which raises the question the rest of this evidence file exists to answer. If the moving thermometer feels heat, what exactly is touching it? To get there, we need three things. First, what temperature actually measures once the particles are gone. Second, the invisible boundary that opens up behind anything that accelerates, and what that boundary does to the idea of empty. Third, the argument, still unresolved after 5 decades, over whether this warmth is real physics or an artifact of the mathematics, and the strange laboratory results that are beginning to force the issue. The file opens with the thermometer itself. Temperature feels like the most ordinary quantity in physics, which is precisely why it fails first. The number on the wall of your room is a summary of motion. Air molecules, each one moving at hundreds of meters per second, several hundred miles per hour, collide with the thermometer and hand over tiny amounts of energy, and the average of that molecular battering is what we agree to call warmth. 20 degrees Celsius, 68 degrees Fahrenheit, is not a substance, it is a census of collisions. Heat what you like, cool what you like, and you are only ever changing how violently the constituents of matter jostle each other. Follow that definition to its edge, and it seems to close the case on empty space. Remove the molecules, and there is nothing left to jostle. No collisions, no census, no temperature. At best, you might say the temperature of a perfect vacuum is absolute zero, minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit, the floor below which no motion remains. That is the clean picture. The universe we actually inhabit refuses to be that clean, and the refusal comes in 2 layers. The first layer is ordinary and already humbling. Space as we find it is never empty. The universe is filled, everywhere, with a thin bath of microwave radiation, light that has been traveling since the cosmos was young, stretched and cooled by expansion until it now sits at 2.725 Kelvin, about 2 3/4 degrees above absolute zero. Physicists know it as the cosmic microwave background, and it has been measured with a precision that borders on obsessive, 2.72548 Kelvin, give or take about 0.5 of a degree. Point any thermometer at the darkest patch of sky between the galaxies and it will not read 0. It will read the cosmic microwave background, the residual warmth of the early universe, arriving from every direction at once. This is real radiation made of real photons, and every observer drifting freely through deep space agrees it is there. The second layer is the one this file is about, and it does not behave like the first. Suppose you could screen out the cosmic microwave background entirely. Suppose you could build a region with no photons, no molecules, no neutrinos, no stray fields, the state physicists call the quantum vacuum, the configuration of the world with everything removable removed. Quantum field theory, the framework that underlies all of particle physics, is unambiguous about what that state is. It is not a void in the older sense. It is the lowest energy condition of a set of fields that fill all of space, fields that cannot be switched off, and whose stillness is never quite still. What we call a particle is a ripple in those fields. What we call nothing is the fields at rest. The question of what a thermometer reads in that nothing turns out to depend on a distinction no thermometer on Earth was ever built to notice: the distinction between sitting still and accelerating. Before I continue, consider what has just happened to the question. You asked for the temperature of an empty room, and the answer has already forced a definition of temperature, a relic of the early universe, and the claim that nothing is a physical system with properties of its own. Take a moment with that last one. The emptiness you picture behind your closed eyes at night, the black gap between the stars, is, in the current accounting of physics, a thing. It has an energy, it has structure. What it does not have, we are about to see, is a temperature that everyone can agree on. The trail actually begins before the effect had a name, in the late 1960s, with a graduate student asking an innocent question about the expanding universe. Between 1966 and 1969, Leonard Parker worked out what happens to a quantum field living in a spacetime that stretches, and found something the textbooks of the day had no shelf for. The expansion itself creates particles. A field that starts in its vacuum state, genuinely empty, does not stay empty while the universe grows. The stretching of space pumps quanta into existence, gently, continuously, out of what was certified as nothing. Parker's result attracted limited attention at the time. Cosmology was not yet the precision science it became, but it planted the seed this entire file grows from. The vacuum's emptiness is not a fixed fact. It is a negotiation between the field and the spacetime the field lives in, and when the spacetime does something dynamical, expand, curve, or, as the next decade would discover, merely host an accelerating observer, the emptiness can fail. Every result ahead of us, the warm detectors, the radiating horizons, the disputed baths, is a variation on Parker's theme, played in a different geometry. The finding did not arrive as a single stroke of insight. It assembled itself across 3 years, in 3 papers, by 3 physicists working 3 separate corners of the same problem, and the order matters because each step removed one more place for the old picture of emptiness to hide. The first step came in 1973 from Stephen Fulling, a young mathematical physicist finishing his doctorate at Princeton under Arthur Wichmann, one of the founders of rigorous quantum field theory. Fulling was studying a question that sounds like bookkeeping and turned out to be a landmine. In quantum field theory, you describe a field by breaking it into modes, elementary vibrations, and declaring which combination of those vibrations counts as the vacuum, the state with no particles. Fulling proved that this procedure is not unique. Perform the quantization in the coordinates natural to an observer at rest, and you get one definition of the vacuum, one census of particles. Perform it in the coordinates natural to a uniformly accelerating observer, and you get a different definition, a different census, and the two do not agree. The state one observer certifies as containing nothing, the other observer's accounting fills with particles. Published in Physical Review D Volume 7, page 2850, the result said something no one had quite said before. In quantum field theory, the word particle does not have an observer-independent meaning. 2 years later, in 1975, Paul Davies, then a young physicist in London with a doctorate from University College London, pushed the calculation into the two geometries where it would matter most. Working in the Journal of Physics A, Volume 8, page 609, Davies computed how a quantized field behaves in the spacetime of a black hole, the Schwarzschild geometry, and in the flat spacetime of a uniformly accelerating frame, the geometry mathematicians call Rindler space. In both cases, the field produced something that looked unmistakably thermal, a spectrum of excitations with the exact statistical shape of heat. This was 1 year after Stephen Hawking had stunned the field by arguing, in Nature and then in Communications in Mathematical Physics, that black holes are not perfectly black, that they radiate with a genuine temperature. Davis's calculation whispered that the black hole might not be the essential ingredient. The thermal character showed up in flat, empty space too, wherever there was acceleration. The final step came in 1976, and it is the reason the phenomenon carries the name it does. William Unruh, born in Winnipeg in 1945, trained at Princeton under John Archibald Wheeler, the same physicist who had mentored Richard Feynman and coined the term black hole, published a paper in Physical Review D titled, with characteristic understatement, Notes on Black Hole Evaporation, Volume 14, page 870. Buried inside it was a construction that changed the question from mathematics to physics. Unruh stopped asking what the field looks like in this or that coordinate system and asked instead what an actual instrument would do. He modeled a detector, an idealized device with internal energy levels, something you could think of as the simplest possible thermometer, and he let it accelerate through the vacuum, the state certified empty by every inertial observer. He then calculated whether the detector clicks. The detector clicks. Unruh's device, dragged through perfect emptiness at constant acceleration, absorbs energy exactly as if it was sitting in a warm gas of particles. Not approximately like a warm gas, but exactly like one. The response follows the precise statistical distribution of thermal radiation, the same mathematical fingerprint you would find in the glow of a furnace, and it comes with a definite temperature attached. That temperature now bears his name, and the formula for it is short enough to say out loud. The Unruh temperature is written T equals h bar A divided by 2 pi c kb. In words before symbols, the warmth an accelerating observer feels from the vacuum is directly proportional to the acceleration and to nothing else. The symbol A is the proper acceleration, the push you would feel in your own frame. The constants around it are the census takers of physics. H bar is the reduced Planck constant, the quantum of action that sets the scale of all quantum effects. The letter C is the speed of light. The final symbol, Kb, is the Boltzmann constant, the conversion factor between energy and temperature, the same constant that governs the air molecules striking the thermometer on your wall. The equation reveals the structure of the claim in one line. Temperature on one side, acceleration on the other. A bridge between them built entirely out of the fundamental constants of quantum mechanics, relativity, and thermodynamics, the three great theories of the 20th century meeting in a single expression barely long enough to fill a breath. The formula is elegant. The numbers it produces are a wall. Divide it out and the exchange rate is roughly 4 times 10 to the minus 21 Kelvin for every meter per second squared of acceleration. Your car, pulling away from a light, accelerates at a few meters per second squared and warms the vacuum around it by a few billionths of a trillionth of a degree. A fighter pilot at 9G, blacking out against the straps, manages about 90 meters per second squared. The vacuum for that pilot glows at less than 4/10 billionths of a billionth of 1 Kelvin. To coax a single degree of warmth out of empty space, 1 Kelvin, you must sustain an acceleration of about 2.5 times 10 to the 20 meters per second squared. Written as g-forces, that is 25 billion g, a 2 and a 5 followed by 18 zeros, roughly a million billion times the acceleration that kills a human being. In imperial units, the figure is no friendlier, around 8 times 10 to the 20 feet per second squared. This single number will follow us through the entire file. Keep it somewhere you can find it again, because every laboratory story we will examine, every laser, every particle beam, every ultra-cold cloud of atoms, is at bottom an attempt to sneak around it. If you are finding a quiet satisfaction in watching an everyday certainty come apart under measurement, this channel does that every week, taking one thing that seems obvious and following the physics until it stops being obvious, and a subscription is the easiest way to keep these investigations arriving. That is the only appeal in this file. The evidence continues. There is a comparison that puts the 2.5 times 10 to the 20 into perspective, and it involves the most extreme, naturally occurring benchmark physics has. Quantum electrodynamics predicts that a strong enough electric field tears the vacuum itself apart, ripping electron-positron pairs out of nothing in a process named after Julian Schwinger. The field strength required, the Schwinger limit, is about 1.3 times 10 to the 18 volts per meter, and the acceleration it corresponds to for an electron is on the order of 10 to the 29 meters per second squared, 10 to the 28 g. That is the acceleration at which empty space stops being a stage and becomes a participant, boiling with matter. The window where physicists hope to detect Unruh warmth cleanly sits between about 10 to the 20 g and that Schwinger ceiling, a corridor 8 orders of magnitude wide. Below it, the effect drowns in cold. Above it, the vacuum shreds. The corridor is narrow, and nothing humans have ever built cruises inside it, at least not yet. Notice too the threshold hiding in our own sky. The cosmic microwave background sets a floor of 2.725 Kelvin everywhere in the real universe. For Unruh warmth to outshine that floor, the linear formula demands just under 7 times 10 to the 20 meters per second squared, between 2 and 3 times the 1 Kelvin figure. Any acceleration below that, and the vacuum's private glow hides beneath the public warmth left over from the early universe. The emptiest place that exists still whispers louder than the effect we are hunting, which is the first hint of how hard the hunt will be, and why, 50 years after the 1976 paper, the direct measurement has never been made. Here is where the file must slow down and do something unusual for this channel, because the temptation at this point is to treat the Unruh effect as an exotic decoration on the edge of physics, a curiosity about impossible thermometers. The record says otherwise. The record says that without this effect, quantum field theory contradicts itself. To see why, we need the invisible boundary, the piece of geometry that appears behind every accelerating object, and that turns out to be the true source of the warmth. We need the horizon. A word about the man whose name the temperature carries, because his path to it explains the paper's strange title. William George Unruh was born in Winnipeg on the 28th of August 1945 into a Mennonite family, took his undergraduate degree in Manitoba and went to Princeton for a doctorate completed in 1971 under John Archibald Wheeler. At the precise moment, Wheeler's students were turning black holes from mathematical embarrassments into the central objects of gravitational physics. Unruh spent his career at the University of British Columbia, later became the founding director of the National Cosmology and Gravity Program at the Canadian Institute for Advanced Research, and was elected a Fellow of the Royal Society in 2001. And the through line of that career is visible in the 1976 paper itself. He was not hunting a curiosity about rockets. He was hunting Hawking's black hole result from the flat space-time side, building the simplest laboratory, even a purely conceptual one, in which horizon warmth could be isolated from gravity and examined on its own. The rocket was the control experiment for the black hole, which is why the phenomenon of accelerated warmth first appears in print under the heading of black hole evaporation, and why the community has never fully settled what to call it. The literature says Unruh effect, Fulling-Davies-Unruh effect, Davies-Unruh effect, acceleration radiation, and several longer permutations that try to distribute the credit across everyone the three-paper history implicates. A small, ongoing negotiation that tells you the discovery was less a bolt from one mind than a structure three minds assembled from different sides. Within the field, its standing is summarized in a phrase specialists use with a straight face. The effect is as well tested as free quantum field theory itself, meaning tested exactly as far as the framework that implies it, and not one measurement further. Start with something you have felt. An elevator rises, and for a moment you are heavier. A plane throttles down the runway, and a hand you cannot see presses you into the seat. Acceleration is the one kind of motion your body detects without instruments, without windows, without reference points. Constant velocity is invisible, which is the heart of relativity. A sealed train car at steady speed feels identical to a parked one. Acceleration is different. Acceleration is felt. Physics honors that distinction with a term, proper acceleration, the acceleration measured in your own frame, the push on your own bones. And it is proper acceleration, not speed, that enters Unruh's formula. The vacuum does not care how fast you are going, it cares that you are being pushed. Now take that push and hold it. Imagine a rocket that accelerates forever, at a constant proper acceleration, never letting up. Relativity will not let it cross the speed of light, so instead the rocket's speed creeps closer and closer to that limit while never reaching it, and its path through space-time bends into a hyperbola, a curve that approaches a straight light-ray line ever more closely and never touches it. Physicists call this hyperbolic motion, and the region of space-time such an observer can ever see has a name, the Rindler wedge, after the physicist Wolfgang Rindler, who developed the coordinates adapted to accelerated observers. The wedge is the accelerating observer's whole world, and its edge is where the strangeness begins. Picture a light signal chasing the rocket. If the signal starts close enough behind, it catches up. The rocket is not yet fast enough to outrun it. The rocket keeps gaining speed forever though, which means there is a line in space-time, a boundary, from beyond which no signal, not even light, will ever arrive. Anything that happens behind that line is permanently outside the rocket's experience, not hidden by distance, hidden by causality. The boundary is called the Rindler horizon, and it behaves, for the accelerating observer, exactly the way the event horizon of a black hole behaves for an observer hovering outside one. Events beyond it can send no message forward. The accelerating observer is causally cut off from an entire region of the universe, a region that an inertial observer, coasting beside the same stretch of space, can see perfectly well. Sit with the asymmetry, because the entire mystery lives inside it. The inertial observer, drifting with no push, sees all of space-time given enough patience. The accelerated observer, simply by virtue of being pushed, has drawn a curtain across part of reality. Nothing dramatic marks the curtain. There is no wall, no glow, no sign. A coasting observer could float across the Rindler horizon of the accelerating rocket and feel nothing at all, the way, in general relativity, a falling astronaut crosses the event horizon of a large black hole without noticing the crossing. The horizon is not a place. It is a relationship between an observer's motion and the causal structure of space-time. Accelerate and part of the universe signs off. Stop accelerating and the curtain lifts. What does a curtain have to do with warmth? Everything, and the connection runs through the deepest property of the quantum vacuum, one we have not yet put on the table. The vacuum of quantum field theory is not merely a lowest energy state, it is a deeply correlated state. The field's values at different points of space are not independent, they are linked, entangled, in the technical sense of quantum mechanics, the same entanglement made famous by paradoxes and prize-winning experiments. Two regions of the vacuum, even regions with nothing in them, share correlations, joint patterns in their fluctuations, and those correlations are not optional decoration, they are load-bearing. Calculations in quantum field theory show that the correlations in the vacuum are, in a precise sense, as strong as the theory allows. The stillness of empty space is a woven stillness, every patch stitched to its neighbors. Now hang the curtain. The accelerating observer cannot receive information from beyond the Rindler horizon. Half of the woven pattern, the half behind the curtain, is causally gone. The vacuum stitches, though, do not respect the curtain, they run right through it. The part of the vacuum the accelerated observer can interact with is one half of an entangled whole, and quantum mechanics has a standard, unavoidable prescription for what happens when you describe half of an entangled system while ignoring the other half. The half you keep no longer looks like a pure, definite state. It looks like a statistical mixture, a state of incomplete information. And the mathematics of that mixture, for the vacuum split by a Rindler horizon, takes a very specific form. It takes the form of heat. This is the mechanism, stated in one pass and worth stating twice. The inertial observer sees the whole tapestry, a single pure quantum state, no particles, no temperature. The accelerating observer is walled off from half of it, and the remaining half, viewed on its own, carries exactly the statistical scatter, the randomness, that defines thermal radiation. The warmth is not added to the vacuum by the acceleration. The warmth is what the vacuum's hidden correlations look like from behind a curtain. Temperature, here, is ignorance with a spectrum. Because the size of the effect is set by how the horizon slices the vacuum's fluctuations, the temperature comes out proportional to the acceleration, precisely Unruh's formula, h bar a over 2 pi c kb. This is the part that stays with me, not because it is exotic, but because of what it does to a word I thought I understood. Heat, in every experience you have ever had, is something present, molecules striking skin, photons arriving from a fire. The Unruh calculation says heat can also be something missing. The accelerated thermometer is not being bombarded by intruders from elsewhere. It is reading the statistical shadow of information it can no longer reach. The glow is an absence, worn like a presence. I return to that inversion often, not for comfort, for clarity about how little our thermal instincts were ever tracking the real bookkeeping underneath. There is a name for the rigorous version of this statement, and it arrived with a precision that startled even the specialists, at almost the same moment as Unruh's paper. In 1975 and 1976, two mathematical physicists, Joseph Bisognano and Eivind Wichmann, working in the austere formalism of algebraic quantum field theory, proved a theorem with no approximations in it. Restrict the Minkowski vacuum, the standard vacuum of flat spacetime, to one Rindler wedge, and the resulting state satisfies the KMS condition with respect to the boost that generates the accelerated observer's time. The KMS condition, named for Kubo, Martin, and Schwinger, is the mathematically exact criterion for thermal equilibrium, the gold standard definition of what it means for a state to be at a temperature. The Bisognano-Wichmann theorem is not a model of a detector, not an approximation, not a plausibility argument. It is a structural fact about quantum field theory itself, proved from the axioms. The vacuum, seen from the accelerated wedge, is thermal in the strictest sense the discipline possesses. Whatever the Unruh effect is, it is not sloppy mathematics. Before we go further, run the numbers against your own life, because the scale deserves to be felt rather than recited. The most violent acceleration you will ever survive is a car crash, on the order of tens of g for a few milliseconds. Call it 100 g to be generous, roughly 1,000 meters per second squared, about 3,200 feet per second squared. The Unruh temperature of that moment is around 4 times 10 to the minus 18 Kelvin, a decimal point followed by 17 zeros before the first digit. The coldest temperatures ever engineered in a laboratory, the ground states of the best ultra-cold experiments, sit around a billionth of a Kelvin, 10 to the minus 9. The warmth your worst day on the road extracts from the vacuum is a billion times colder than the coldest cold humans have ever manufactured. The effect is not small the way a whisper is small. It is small the way a single atom is small against the mass of a planet. And yet, as we are about to see, the theory cannot survive without it, which is its own kind of message. Reality appears to keep books at a resolution absurdly finer than anything we can read, and it balances them even where no one can check. What would you conclude from this evidence so far? A formula ties temperature to acceleration through 3 fundamental constants. A theorem certifies the warmth as mathematically genuine thermal equilibrium. A number, 2.5 times 10 to the 20 meters per second squared per Kelvin, guarantees that no direct instrument has ever felt it. The mathematics is airtight and the thermometers are silent. And between those two facts runs a fault line that has divided serious physicists for 50 years. Written with one substitution, it is the equation of a black hole, and the substitution is the reason most physicists believe the Unruh effect is not optional. The horizon we built with acceleration has a gravitational twin, and the twin radiates. In 1974, 2 years before Unruh's paper, Stephen Hawking published a short article in Nature, volume 248, page 30, with a title that ended in a question mark: Black hole explosions? The calculation behind it, laid out fully the following year in Communications in Mathematical Physics, volume 43, page 199, treated a quantum field in the curved spacetime around a collapsed star, and it produced the most famous result of late 20th century physics. A black hole is not black. The horizon, the boundary of no return, forces the quantum fields around it into a state that radiates, faintly but genuinely, with a perfect thermal spectrum. The radiation now bears Hawking's name, and its temperature is set by a single property of the whole, a quantity called surface gravity, written kappa, which measures how hard the horizon pulls at its own edge, the gravitational analogue of an acceleration. The Hawking temperature is written T equals h bar kappa divided by 2 pi CKB. Say the two formulas back to back and let the repetition do its work. The Unruh temperature, h bar a over 2 pi CKB, where a is the proper acceleration of an observer. The Hawking temperature, h bar kappa over 2 pi CKB, where kappa is the surface gravity of a horizon. They are the same expression. One symbol swaps its costume, acceleration for surface gravity, and everything else, every constant, every factor of 2 pi, stands unchanged. Earlier in this file I said the match would matter, and this is the moment it becomes the hinge of the whole subject. The equation governing the slow death of a black hole and the equation governing a thermometer waved hard through the dark are one equation. Nature does not repeat a formula that exactly by accident, and physicists have spent 5 decades unpacking what the coincidence that is not a coincidence means. For a black hole with the mass of the Sun, the numbers land with a strange gentleness. Rewriting the surface gravity in terms of mass, the Hawking temperature becomes h bar c cubed over 8 pi gmkb, inversely proportional to the mass, and for one solar mass it evaluates to 6.17 times 10 to the minus 8 Kelvin. 62 billionths of a degree above absolute zero. Hold that against the number this file established at the start, the 2.725 Kelvin of the cosmic microwave background that fills every corner of the real universe. And the comparison is almost embarrassing. 44 million times colder than the ordinary afterglow of the sky, that is the radiation of a solar mass black hole. A black hole of 30 solar masses, the kind whose collisions are gravitational wave detectors here, sits colder still, near 2 billionths of a Kelvin, Its total Hawking output a luminosity around 10 to the minus 31 watts, a number so small it has no honest comparison in engineering. A firefly outshines it by more than 28 orders of magnitude, which yields one of the quietest facts in astrophysics. Every stellar black hole in the present universe is colder than the sky around it, and heat flows from hot to cold, so every one of them is absorbing more energy from the cosmic microwave background than it gives back. They are not evaporating, they are feeding, gaining mass from starlight and relic radiation, and they will continue to feed for as long as the universe stays warmer than they are. The famous evaporation, the black hole ending in a whisper of radiation, belongs to a future so remote that the expansion of the universe must first cool the sky below billionths of a degree. The mechanism is real. The schedule is longer than every process you have ever called slow, stacked end to end. Not tragic, just the bookkeeping of two temperatures, one of which our own file has already measured against the other. Here is what the identity of the two formulas buys, and why Unruh's 1976 paper carried the title Notes on Black Hole Evaporation rather than anything about rockets. Hawking's calculation lived in curved spacetime, technically formidable, physically strange, and in the 1970s it needed independent confirmation from a direction that did not require trusting a black hole. Unruh supplied the direction. Consider an observer hovering just above a black hole's event horizon, engines screaming, holding position against gravity. Close to the horizon, that observer's proper acceleration grows without bound, and a theorem of general relativity, the equivalence principle, says that locally, in a small enough patch, gravity and acceleration are indistinguishable. Near the horizon, the curved Schwarzschild geometry flattens, in the mathematical limit, into exactly the Rindler geometry of a uniformly accelerated observer in empty space. The metric of one deforms continuously into the metric of the other. The horizon of the black hole and the horizon of the accelerating rocket become, locally, the same object. Run the logic through. The hovering observer is accelerating, and by Unruh's result, an accelerating observer in the vacuum feels warmth proportional to that acceleration. Take the Unruh temperature felt just above the horizon, then account for the climb, the gravitational redshift that stretches and cools any radiation as it fights its way out of the hole's gravity to a distant astronomer. The near-horizon acceleration works out to 1 over 4m in natural units. The redshift does its arithmetic, and the temperature received far away comes out as 1 over 8 pi m. That expression, translated back into ordinary units, is precisely the Hawking temperature. Two derivations, one starting from gravity and quantum fields in curved spacetime, one starting from acceleration and quantum fields in flat spacetime, arrive at the same number from opposite ends. The Unruh effect is not an imitation of Hawking radiation, it is the local engine of it. Hawking radiation, seen through this lens, is the Unruh effect wearing a gravitational field. The kinship extends further, into a third setting that completes the pattern. In 1977, Gary Gibbons and Stephen Hawking showed that an observer in an accelerating, expanding universe, the de Sitter spacetime our own cosmos increasingly resembles, is also surrounded by a horizon, a cosmological one, and that horizon too carries a temperature, now called the Gibbons-Hawking temperature. 3 horizons, 3 settings, 1 formula. Accelerate through flat emptiness, hover near collapsed matter, or simply exist in an accelerating universe, and in each case a boundary appears in what you can ever see, and with the boundary comes heat. The lesson assembling itself across these results is stark. Wherever causality draws a curtain, thermodynamics collects a fee. Temperature, in the deepest formulation physics currently has, is not about substance at all. It is about horizons, about the parts of reality an observer's own condition renders unreachable, and about the statistical residue the unreachable part leaves behind in what remains. The family has two more members worth naming, because they mark the boundaries of the claim. The dynamical Casimir effect, confirmed in superconducting circuits in 2011, produces real photons from the vacuum by shaking a boundary, a mirror, fast enough. A cousin phenomenon where the moving element is a physical surface rather than an observer. The Schwinger effect, still undetected in its pure form, would tear electron-positron pairs directly out of the vacuum with a strong static electric field. The 10 to the 18 volts per meter threshold this file already crossed. Both are vacuum instability phenomena. Both are siblings of the Unruh mechanism in the family portrait of quantum field theory, and both underline the same message from different angles. The vacuum is not a passive nothing. It is a medium with a breaking strain, a stitched fabric that responds when you shake it, curve it, or race through it. The question this file now has to face is whether the specific response Unruh predicted, the thermal glow of pure acceleration, has ever actually been caught responding. And the first place physicists looked was the strangest paradox classical physics ever produced. An electric charge, shaken, is supposed to shine. For 50 years, no one could agree on who sees the light. Classical physics has known since the 19th century that an accelerated electric charge radiates. The result is quantified in the Lama formula, and it deserves its plain words statement first. The power an accelerating charge pours into electromagnetic waves grows with the square of its acceleration, so doubling the shake quadruples the shine. Spoken as symbols, the power P equals mu0 q squared a squared, divided by 6 pi c, where q is the charge, a is the acceleration, mu0 is the magnetic constant of the vacuum, and c is the speed of light. Every radio tower on Earth is an industrial application of this formula. Electrons shaken along an antenna radiate, your receiver catches the ripples, and the equation has been verified so many times it functions as infrastructure. Now stage the paradox, which begins as a puzzle about gravity and becomes a puzzle about who is allowed to see light. Einstein's equivalence principle says that standing in a gravitational field is locally indistinguishable from accelerating in empty space. A charge sitting on a table in your room is, in that local sense, an accelerated charge. It is being pushed off its natural free-fall path by the floor. Should it therefore radiate? Radio waves from every charged speck of dust forever powered by nothing? Obviously not, and it does not. Turn the puzzle around. Take a charge in genuinely uniform acceleration through empty space. The Lama formula, applied by an inertial observer watching it pass, says it plainly radiates. Climb aboard instead, ride alongside the charge in its own accelerated frame, and the charge simply hangs there, motionless relative to you. A motionless charge, by every law you know, does not radiate. One charge, one history, and one observer collects light from it. The co-moving observer collects none. Both cannot be right, unless the question who saw the radiation has stopped having a single answer. The resolution took decades to converge, and its first half is pure geometry, delivered in its sharpest form by David Boulware in 1980 in Annals of Physics, volume 124, page 169, building on earlier work by Fritz Raulich. Track where the radiation of a uniformly accelerated charge actually goes, field line by field line, and the answer is surgical. All of it flows into the region of spacetime beyond the Rindler horizon of the accelerating frame. Every photon's worth of Lama shine ends up precisely in the territory the co-accelerating observer is causally cut off from. The rider sees no radiation because the radiation, all of it, is emitted into the part of the universe the rider's own motion has curtained away. Nothing is suppressed, nothing is cancelled. The light is real, and it is delivered in full to an address the rider cannot visit even in principle. Radiation, the conclusion runs, is not an absolute concept. Whether light was emitted is a question whose answer depends on the observer's state of motion, because the horizon decides which patches of spacetime are on an observer's map at all. The second half of the resolution is quantum, and it is the micromechanism most treatments skip, which is a loss because it is where the Unruh effect stops being philosophy and starts doing engineering. In 1992, Atsushi Higuchi, George Matsus, and Daniel Sudarsky published a pair of calculations in Physical Review D, volumes 45 and 46, asking what the accelerated frame's version of the Larmor shine is. In the inertial frame, the story is standard. The charge emits ordinary photons. Translate that story, event by event, into the accelerated frame, where the Unruh bath is part of the furniture, and each inertial frame photon corresponds to something almost comically mundane, the emission or absorption of a photon with zero energy into or out of the thermal bath. Zero-energy Rindler photons. In the rider's frame, the charge is not shining. It is trading infinitesimally soft quanta with the warm vacuum it sits in, the way a body in equilibrium with a bath exchanges heat without any net drama. Sum the exchange rates, transform back, and the inertial observer's photon count reappears exactly, at every transverse momentum. The books balance to the last entry, but only, and this is the load-bearing clause, only if the bath is there to trade with. Remove the Unruh bath from the accelerated frame's accounting, and the frames disagree about a measured photon flux. In 2019, André Landolfo, Stephen Fulling, and George Matsus closed the loop with a further calculation in Physical Review D, volume 100, showing the full classical Larmor radiation can be reconstructed from the Unruh bath picture through those zero-frequency modes. The paradox of the shining charge is not merely consistent with the Unruh effect. The paradox is unsolvable without it. There is a companion result, older and stranger, from Unruh himself with Robert Wald in 1984, in Physical Review D, volume 29, page 1047, and it earns its place here because it answers the objection you may already be forming, that all this frame translation is just words. Suppose the accelerating observer's detector clicks, absorbing what that observer describes as one warm particle from the Unruh bath. What does the inertial observer, watching the same physical event, record? Unruh and Wald computed it. The inertial observer records the detector emitting a photon and gaining internal energy while doing so. Absorption in one frame is emission in the other, and both descriptions are complete and correct in their own terms. Even the direction of an energy exchange, the difference between receiving and giving, turns out to be frame-dependent bookkeeping laid over a single invariant event. The event is real. The story told about it bends with the observer's motion, and quantum field theory holds all the stories consistent with a precision that leaves no slack for the bath to be fictional. Step back to the room you are sitting in, because the file has drifted far from it, and the drift is the point. Every certainty this investigation has dismantled so far, one temperature per place, one particle count per state, one answer to did the charge radiate, failed for the same reason. Each of those quantities silently assumed a universal observer, a view from nowhere that every instrument would share. The mathematics keeps returning the same correction. There is no view from nowhere. There are only world lines, individual paths through space-time. And the physics an instrument records is a joint property of the world and the path the instrument takes through it. Your own path, right now, reading this in a chair, pinned at 1G by the floor, is mild enough that all the observer-dependent effects agree to within nothing, which is why the illusion of absolute temperature has held for the entire history of your species. The illusion is not wrong because your life violates it. It is wrong because it fails at the edges, and physics has learned, repeatedly and expensively, that the edges are where the truth lives. The edges, in this subject, produce one more inversion before the file turns to the laboratory. It concerns not empty space, but the ordinary warm universe, and it answers a question with real experimental stakes. What does an already warm background look like to a detector moving through it at nearly the speed of light? Intuition suggests hotter, blue-shifted, more violent. In 1995, Jules Coster and George Matsas calculated the response of an ultra-relativistic detector moving through an ordinary thermal bath and found the opposite. Time dilation slows the detector's internal clocks so drastically that it effectively decouples from the bath's photons, its absorption shifted toward modes the bath barely populates. Fast objects, in this precise operational sense, run cold. A detector streaking through a 300 Kelvin laboratory couples to that ambient warmth orders of magnitude more weakly than a slow one. The result reads like a curiosity until you notice what it does for the experimental hunt. The great fear of any Unruh measurement is that the real thermal universe, the lab, the cosmic microwave background, will drown the vacuum's whisper. The Coster-Matsas mechanism says extreme motion itself turns down the ambient noise, while the Unruh signal, which depends on proper acceleration rather than velocity, remains. The universe, for once, tilts the table toward the experimenter, and it is time to meet the experimenters. Before the file moves to the laboratories, it needs one more piece of anatomy on the table, because every detection scheme ahead rests on it. What, physically, does the accelerated thermometer touch? The answer is fluctuation, and fluctuation can be made precise. Even in its ground state, a quantum field is not quiet. The electric field of the vacuum, measured at any point, averages to zero, but its square does not. The field trembles about zero with an irreducible quantum jitter. And the meaningful physical object is the correlation of that jitter with itself across time, what physicists call the two-point function or autocorrelation function. Ask how the vacuum's trembling at one moment relates to its trembling a split second later along your own path, and you have asked the question whose answer contains everything an instrument riding that path can ever feel. For an inertial path, the answer is the bland, scale-free hiss of the undisturbed vacuum, and detectors tuned to it register nothing, which is why your room reads empty. For a uniformly accelerated path, Chen and Tajima wrote the answer down explicitly, and its shape is the entire experimental program in one expression. The correlation of the vacuum electric field along the accelerated world line is proportional to the fourth power of the acceleration divided by the fourth power of the hyperbolic sine of a tau over 2c, where tau is the time between the two samplings as the mover's own clock counts it. Two features of that formula matter more than its details. The hyperbolic sign in the denominator is the mathematical signature of thermality, the same function that governs correlations in any genuinely hot medium, quantum field theory's way of certifying that the jitter along an accelerated path is organized like heat and not merely amplified like noise. The fourth power of acceleration in the numerator, meanwhile, is the experimenter's despair and hope in one factor. Despair because modest accelerations render the effect invisible beyond all remedy. Hope because the steepness works both ways. Every doubling of acceleration multiplies the touchable signal 16-fold, so the payoff for reaching extreme regimes grows explosively rather than linearly. This is why the hunt concentrated where it did. A fourth power law does not reward patience or cleverness at low acceleration. It rewards violence, and the machinery of violence is what the next exhibits are. One number from the ultra-cold end of the field makes the stakes of that fourth power concrete. The Chicago group, in the paper this file will reach shortly, stated the requirement from their side of the ledger with disarming plainness. An enormous acceleration of 2.5 times 10 to the 14 meters per second squared would be required, they noted, to produce Unruh radiation at a temperature of just 1 microkelvin, a millionth of a degree. Their condensate, by simulating the transformation rather than performing it, sidestepped a demand that no mechanical system on Earth can meet. Keep the number beside its larger sibling, 2.5 times 10 to the 20 for a full Kelvin, and the linearity between them is Unruh's formula doing its bookkeeping across 6 orders of magnitude, the same exchange rate at every scale, warmth per acceleration, fixed by 3 constants and no free parameters anywhere. A theory with no dials to turn is a theory that can be killed by a single honest measurement, which is the highest compliment experimental physics knows how to pay, and the file now turns to the half-century of attempts to deliver one. The strongest single argument that the Unruh bath must be real involves no lasers and no thermometers. It involves a proton and a decay that is forbidden, and it was published in 2001 by Daniel Van Zelle and George Matsys, 2 theorists at the Instituto de Física Teórica in São Paulo, in Physical Review Letters, Volume 87, Article 151301. If this file could keep only one exhibit, it would keep this one. A proton at rest is, as far as every experiment can tell, stable. Its decay into a neutron, a positron, and a neutrino is forbidden by energy conservation. The neutron is heavier, and the books do not balance. The known process runs the other way. A free neutron decays into a proton in about 15 minutes. The energy books change for an accelerated proton though, because an accelerated particle has an energy reservoir to draw on, the agent doing the accelerating. Standard quantum field theory, worked out in the inertial frame with the ordinary machinery of the weak interaction, predicts that a sufficiently accelerated proton can decay, converting into a neutron, a positron, and a neutrino, with a definite, calculable lifetime. The calculation is unremarkable in method, no horizons, no Rindler wedges, no Unruh anywhere. It is the kind of computation done 1,000 times a year, and it yields a number. Now perform the same physics in the proton's own frame, the frame riding along with the acceleration, and watch the problem lock up. In its own frame, the proton is at rest, and a proton at rest cannot decay. The energy is not there. Every path to the neutron is closed, and yet the inertial calculation just promised, with textbook methods, that the decay happens. A particle's survival cannot depend on who files the paperwork. Either the proton decays or it does not. Both frames must agree on whether a neutron eventually exists, and the co-accelerated frame has no way to pay for one, unless something in that frame supplies the missing energy. Van Zelle and Matsys carried out the co-accelerated calculation in full, and there is exactly one way it produces a decay at all. The proton must be immersed in the Unruh thermal bath, and the decay proceeds because the proton absorbs quanta from that warmth, the bath itself lifting the books into balance. Include the bath, and the co-accelerated frame predicts a decay lifetime. Compare it with the inertial frame's answer, computed by entirely different mathematics with entirely different intermediate objects, and the 2 lifetimes agree exactly. Read the logic of that agreement the way a court would. The inertial calculation used no Unruh effect and got a number. The accelerated calculation is impossible without the Unruh effect, and with it gets the same number. The bath is therefore not an optional interpretation bolted onto quantum field theory. It is the only thing that keeps quantum field theory from contradicting itself between 2 frames about a yes or no physical fact, whether a particle died. Van Zelle and Matsys stated the conclusion without hedging, and their sentence deserves quoting in full, because its bluntness is a data point about how specialists rank this evidence. The Fulling-Davies Unruh effect, they wrote, is mandatory for the consistency of quantum field theory. There is no question about its existence, provided one accepts the validity of standard quantum field theory in flat spacetime. Pause on what kind of claim that is, because science has a specific category for it, and the category carries weight. The effect has never been observed directly, and yet its status is being asserted not from observation, but from consistency. The same species of argument that made physicists certain about antimatter before the positron was found in a cloud chamber, certain about the neutrino decades before one was caught. When a framework that passes every test you can perform also says that its own coherence requires an as-yet unseen phenomenon, the phenomenon inherits the credibility of the framework. That is precisely the inheritance the Unruh effect lives on. Quantum field theory in flat spacetime is the most stringently tested structure in the history of measurement. Its predictions for the electron's magnetic moment verified to parts in a trillion. The Unruh bath is not a speculative garnish on that structure, it is load-bearing wall, and the specialists who dismiss it understand that they are proposing renovations to the entire building. Some of them, as this file will document shortly, propose exactly that, and they are not cranks. Hold the tension, it is the honest condition of the subject. Before the laboratory evidence, one more pass at the human scale, because the file is about to spend a long stretch among giga-electron volts and petawatts, and it should leave from familiar ground. Tonight, at some point, you will lie down, and the room will go dark and quiet. And if the house is still enough, you will be as close to an inertial observer as your life permits, carried smoothly along Earth's orbit, pressed by nothing but one gentle G. The vacuum around your bed, by everything this file has established, is for you at its coldest and emptiest, a woven stillness with no senses of particles at all. The version of you that could feel it glow, the you accelerated at 25 billion G, is not a physical possibility. No bone, no atom of you survives a millionth of that. The warmth of empty space is real enough to hold quantum field theory together, and it is locked behind a door no living thing can pass. Whatever finally reads that temperature will be an instrument, built precisely because our bodies were never going to be invited. The rest of this file is the story of those instruments, the 5 decades of attempts, the one that ended in an ultra-cold cloud of atoms in Chicago agreeing with Unruh's formula, and the ongoing argument about whether any of it counts. Consider, before the instruments parade past, what you would accept as proof. Set your own threshold now, privately, because the exhibits ahead are designed by nature to sit just under every comfortable standard. There will be spin measurements that carry the signature indirectly, reinterpretations of old data that claim the signature outright, and quantum simulations that reproduce the mathematics faithfully in a different medium. None of them is a thermometer on a rocket. Whether any of them is enough is a question the physics community itself has not settled, and by the end of the file, the judgment will, in part, be yours. The first serious proposal to catch the vacuum glowing came not from a purpose-built experiment, but from a machine physicists were already running for other reasons, and it began with a conversation between two unusual minds. John Stuart Bell, the Northern Irish theorist whose inequalities later won the 2022 Nobel Prize for the physicists who tested them, spent his career at CERN, officially working on accelerator physics, treating the foundations of quantum mechanics as a Sunday discipline. In the early 1980s, with the Norwegian physicist John Magne Leinas, Bell asked a question nobody had thought to ask of the great storage rings. Are they already Unruh detectors? A storage ring holds electrons on a circular track at nearly the speed of light, and circular motion at constant speed is still acceleration, centripetal acceleration, pointed at the center, felt in the electron's frame as a relentless sideways push. The numbers are enormous by any laboratory standard. In the large electron-positron colliders regime, the centripetal acceleration reaches about 2.9 times 10 to the 23 meters per second squared, 3 orders of magnitude beyond the 1 Kelvin threshold this file flagged and asked you to keep. Feed it through Unruh's formula naively, and the vacuum, for those electrons, glows at roughly 1200 Kelvin, hotter than the surface of Venus, hotter than boiling lead. For once, the effect is not microscopically cold. The question becomes what part of the electron could serve as the thermometer. Bell and Leinas answered, the spin. An electron is a tiny magnet, and in the ring's magnetic field, its spin can point with the field or against it, 2 orientations separated by a small energy gap. A perfectly cold electron population would settle entirely into the lower orientation, complete polarization. A warm environment, any warm environment, kicks some spins into the upper orientation, and the fraction that ends up excited is a thermometer reading in disguise. Accelerator physics already possessed the relevant result. Arseny Sokolov and Igor Turnov had shown in the 1960s that electrons in a storage ring polarize spontaneously but never completely, saturating at a maximum polarization of 8/5√3, about 92.4%. A figure later confirmed beautifully at the Spear ring at Stanford at around 3.6 gigaelectronvolts. The missing 7.5% was understood as an unavoidable quantum effect of the radiation the electrons emit. Bell and Leynas reinterpreted it. The failure to fully polarize, they argued, can be read as the spins being warmed, agitated out of their ground state by the thermal environment that circular acceleration creates, the circular cousin of the Unruh bath. The depolarization measured in real rings on this reading is the vacuum's warmth expressed in electron spins. The interpretation is genuinely contested terrain, and the file must be precise about why, because the caveat teaches more physics than the claim. Unruh's clean theorem applies to uniform linear acceleration, whose horizon structure produces an exact thermal state at an exact temperature. Circular motion is different. The rotating frame has no true horizon of the Rindler kind, and when Bell, Leynas, and later workers computed the effective temperature felt by the circling spin, it came out close to the Unruh value but not equal to it. And worse, it depends on details, on the velocity as well as the acceleration, and on which internal transition you use as the probe. Circular vacuum noise, as the specialists put it, is not universal. A single number cannot summarize it the way a single temperature summarizes a true thermal bath. The storage rings end up delivering a maddening verdict. Something in the vacuum demonstrably agitates accelerated spins. The agitation tracks the acceleration. The measured 92.4% ceiling matches calculations in which vacuum fluctuations in the accelerated frame do the agitating, and yet the phenomenon is a cousin of the Unruh effect, rather than the effect itself. Close enough to be encouraging, different enough that skeptics can decline to count it. The first exhibit ends unresolved, which sets the pattern for nearly everything that follows. The second exhibit trades magnets for light, and it begins in 1999 with a proposal in Physical Review Letters, Volume 83, page 256, by Pizin Chen of Stanford's Accelerator Laboratory and Toshiki Tajima, the plasma physicist who had co-invented laser Wakefield acceleration 2 decades earlier. Their idea was blunt. If the obstacle is reaching 10 to the 20 meters per second squared, stop trying to accelerate objects and start using the most violent force fields humans can generate, the electric fields inside ultra-intense laser pulses. Focus a petawatt-class laser to a spot a few millionths of a meter wide, and the oscillating electric field grades into the range of 10 to the 15 volts per meter. An electron caught in that field is thrown back and forth so hard that its peak proper acceleration can graze 10 to the 25 g, comfortably inside the corridor between the Unruh threshold and the Schwinger ceiling that this file mapped earlier. The laser community measures this violence with a dimensionless number, the laser strength parameter A0, the ratio of the field's push to the electron's own mass scale. And for the wavelengths of titanium-sapphire systems, around 800 nanometers, each unit of A0 corresponds to roughly 2.3 times 10 to the 22 g of peak acceleration. Modern systems reach A0 in the tens and hundreds. On paper, the acceleration problem is solved. The signal problem replaces it, and the signal problem is severe. An electron shaken that hard is a lighthouse of ordinary radiation, the Lama shine this file has already dissected, and the rare, soft photons scattered out of the Unruh bath must be found against that glare. Chen and Tajima computed the Unruh signature directly from the vacuum's autocorrelation function in the accelerated frame, the statistical fingerprint the warmth leaves on the electric field and accelerated charge samples, and they identified their advantage in geometry. The Lama glare, for extreme relativistic oscillation, is beamed into narrow forward lobes, and there exists a blind spot, a thin angular region, azimuthal width around 1 part in 1,000, where the classical shine drops steeply while the Unruh-derived scattering does not. Sit a detector in the blind spot, integrate over many shots, and the thermal whisper could in principle rise above the classical roar, with a further check available in how the two signals scale differently with laser power and angle. That is the theory. The proposal has waited a quarter century for a machine worthy of it, and the machine now exists as a continental project. The Extreme Light Infrastructure, a European facility distributed across 3 sites, ELI Beamlines near Prague, ELI Alps in Szeged, and ELI NP in Magurele, Romania, funding approved in 2011 and 2012, hosts the most powerful lasers ever constructed, including twin 10 petawatt systems at the nuclear physics pillar in Romania. Design intensities run from 10 to the 23 watts per square centimetre upward, with the Prague site's flagship chamber aspiring toward 10 to the 25, and the facility's own scientific documentation lists Unruh physics by name among its target phenomena. One comparison from the ELI literature compresses the stakes into a single sentence. An electron at the focus of such a laser experiences accelerations comparable to those at the event horizon of a black hole of 6 times 10 to the 18 kilograms, the mass of a modest asteroid belt compacted below its own Schwarzschild radius. The apparatus for interrogating horizon physics without a horizon is operational. Commissioning experiments are underway, and no Unruh detection has been announced. The corridor is open. The whisper has not yet been separated from the roar, and the community's attention has partly shifted to a stranger venue, a place where the accelerations dwarf even the lasers, inside the atomic lattice of a crystal. 2 equations frame the corridor the laser hunters work inside, and both deserve their spoken form before the file proceeds, because they are the fence posts of the entire strong field program. The ceiling is Schwinger's. The critical electric field at which the vacuum itself breaks down is written ES equals me squared c cubed over EH bar, the electron mass squared, times the speed of light cubed, divided by the elementary charge times the reduced Planck constant. Only fundamental constants enter, which is the point. The vacuum's breaking strain is a property of nature, not of apparatus, and it evaluates to about 1.3 times 10 to the 18 volts per meter. Fields beyond it do not merely accelerate charges, they conjure them, tearing electron-positron pairs from the vacuum faster than any process can be read cleanly. The floor, for practical purposes, is set by the laser community's working measure of violence, the strength parameter A0, defined as EE0 over MC omega 0, the charge times the field amplitude, divided by the electron's mass times the speed of light times the laser's frequency. In words, A0 counts how many times its own rest energy the field can pump into an electron within a single optical cycle. Below 1, electrons quiver politely. Above 1, they are hurled at relativistic speeds each half cycle, and every unit of A0, for the standard 800 nanometer titanium sapphire wavelength, buys about 2.3 times 10 to the 22 grams of peak proper acceleration. Between the A0 of the biggest operating lasers and the Schwinger ceiling stretches the 8 order of magnitude corridor this file mapped hours ago, and it is worth saying plainly what the 2 fence posts mean together. Humanity's most violent instruments have finally grown tall enough to reach the corridor's floor, and the corridor's ceiling is where the question stops being measurable at all, because past it the vacuum answers every experiment with a blizzard of matter. The window for reading the void's temperature is not just narrow, it is the only window there will ever be. fixed by the constants of nature on both sides, and the machines have arrived at its sill within living memory of the prediction they came to test. On the Marin campus of CERN, far from the cathedral-sized detectors of the Large Hadron Collider, an experiment called NA63 has spent 2 decades doing something that sounds almost quaint. It fires particles at crystals. Led by Ulrik Ugerhøy of Aarhus University in Denmark, NA63 takes electrons and positrons from the superproton synchrotron at energies from 50 gigaelectron volts up toward the 200 mark, and steers them into thin wafers of silicon, germanium, and tungsten whose atomic planes have been aligned, with exquisite care, almost parallel to the beam. When the alignment is right, a particle does not crash through the lattice at random. It channels, gliding down the corridor between atomic planes, and the summed electric fields of the ordered atoms grip it continuously. The fields inside matter, seen this way, are ferocious. In the particle's own rest frame, boosted by a Lorentz factor of order 10 to the 5, the crystalline field strengthens to the range of 10 to the 10 and 10 to the 11 volts per centimeter, at and beyond the Schwinger critical field, where the vacuum itself becomes unstable. A tabletop wafer, entered at the correct angle and speed, briefly outmuscles every laser on Earth. The accelerations follow. A channeled electron at Na63 energies experiences proper accelerations in the range of 10 to the 24 meters per second squared and beyond, 10,000 times the 1 Kelvin Unruh threshold, corresponding to vacuum temperatures that are not merely measurable but violent, 10,000 Kelvin and upward, hotter than the surface of the Sun. The experiment's original purposes were solid and unexotic, precision studies of radiation emission in strong fields, and in that role, Na63 has delivered landmark results, including the first clean measurements of quantum radiation reaction, the regime where the light a particle emits kicks back on the particle hard enough to change its subsequent motion, published in Nature Communications in 2018 and Physical Review Letters in 2020. The datasets are public, the spectra precise, and for most of 2 decades nobody read them as horizon physics. Then, beginning in 2022, a theorist named Morgan Lynch did. In a series of papers, the most recent published in Physical Review D, volume 112, in October 2025, Lynch and collaborators reanalyzed the Na63 radiation spectra with the machinery of accelerated frame thermodynamics, and made a claim of a completely different order. In the high-energy region of the photon spectrum, above a threshold near 22 gigaelectron volts, where the emission becomes dominated by the recoil of the radiating particle, the measured spectra, they argue, match the profile of thermal emission at the Fulling-Davies Unruh temperature of the channeled particle's acceleration. Not approximately match, in their accounting, but saturate the thermal component filling the spectrum across all analyzed datasets. Lynch's papers describe the result as a measurement of the recoil Unruh temperature and, in the boldest formulation, as an experimental observation of a Rindler horizon, the causal curtain this file built in its first hour, allegedly leaving fingerprints in a Danish group's crystal data. The claim has not conquered the field, and the reasons are instructive rather than dismissive. A reinterpretation of existing data inherits every systematic ambiguity of the original experiment, plus new ones of its own, and the Na63 spectra were neither designed nor instrumented to discriminate a thermal Unruh component against the many strong field radiation processes that populate the same energy range. The channeling environment is not clean, uniform acceleration. The fields vary along the particle's path. The acceleration is transverse and oscillatory rather than constant and linear, and the same non-universality that haunts the storage ring interpretation haunts the crystal one. Independent groups have not, as of the most recent literature this file draws on, reproduced the analysis with a consensus verdict. What can be said neutrally is this: the most extreme sustained accelerations available to experiment occur inside aligned crystals. the radiation from those accelerations has been measured with precision, and at least one published, peer-reviewed line of analysis finds the Unruh temperature written in it. The claim is on the record in a mainline journal, awaiting the ordinary machinery of scientific digestion, replication, refutation, or refinement. 50 years into this subject, that is the closest thing to a direct detection anyone has put on paper, and it arrived not from a machine built for the purpose, but from someone rereading old light with new eyes. While the strong field community argues over crystals, a different community approached the problem from the opposite temperature extreme, and in 2019, it produced the cleanest laboratory sentence in this entire file. At the University of Chicago, in the group of Cheng Qin, physicists Jiazong Hu, Lei Feng, and Zhendong Zhang built an experiment out of the coldest matter humans can make, a Bose-Einstein condensate, roughly 60,000 cesium atoms cooled until they merge into a single collective quantum state, held in a disc-shaped trap 13 micrometers across and 1 micrometer thick, a wafer of matter thinner than a red blood cell. A condensate is not empty space, and no one pretended otherwise. It is a quantum field you can build, a medium whose collective excitations, its phonons, obey equations with the same mathematical structure as the quantum fields of the vacuum. The strategy, part of the broader program called analog gravity, is to engineer in the condensate the same transformation that acceleration performs on the true vacuum, and then check whether the predicted thermal statistics appear, with every step observable, because unlike the real vacuum, a condensate lets you photograph its fluctuations directly. The Chicago team drove their condensate with a precisely modulated oscillation, shaking the trap in a pattern mathematically equivalent to the frame transformation of an accelerated observer, and then imaged what the matter field did. It did what Unruh said it must. Thermal fluctuations bloomed out of the condensate's quantum ground state, matter wave noise with the exact statistical distribution of a thermal bath, at a measured temperature of about 2 microkelvin, and the paper's own language, published in Nature Physics, Volume 15, page 785, is unusually direct for the genre. We observe radiation at 2 microkelvin, the authors wrote, and the measurement excellently agrees with the Unruh prediction. 2 signatures elevated the result above a mere noise measurement. The fluctuations showed long-range phase coherence across the cloud, and they exhibited a temporal reversal behavior, both hallmarks of the entangled pair production mechanism underlying the effect, and both inconsistent with garden-variety classical heating. Cheng Qin, describing the work to the press, called it a hidden connection to a gravitational phenomenon, Unruh radiation, made visible in a system 60,000 atoms small. The catalogue of such quantum simulations is now a field of its own. A nuclear magnetic resonance simulator reproduced the effect's core transformation in 2016 in the journal Science China Physics. Trapped ion platforms have implemented oscillatory versions, with the ion's motion standing in for the accelerated worldline, including recent designs that place the simulated detector in quantum superpositions of different trajectories, an experiment impossible in principle with a rocket. Superconducting circuit proposals couple a flux qubit, a loop of current that can serve as a 2-level Unruh DeWitt detector, to a microwave resonator whose vacuum can be effectively boosted. Each platform validates the same lesson from a different substrate. Wherever the mathematics of the accelerated vacuum can be physically instantiated, the thermal statistics appear on schedule, at the predicted effective temperature, with the predicted entanglement structure. What none of these systems contains is the actual vacuum of spacetime. They are faithful executions of the equations in borrowed matter, and how much they prove about the real thing is precisely the kind of question this file has learned to leave standing. An analogue of a glow is not a glow, says the skeptic. The equations do not know what they are made of, says the believer. Both sentences are true, and the space between them is where this subject lives. The condensate experiment did not appear from nowhere, and its lineage closes a circle this file opened hours ago, because the founder of the lineage is the same physicist whose name the effect carries. In 1981, William Unruh, having spent 5 years watching his prediction sit untouchable behind its 25 billion G, asked the question that created a field. If the real vacuum cannot be interrogated, can another medium be found whose excitations obey the same equations so that the interrogation can proceed by proxy? His answer was sound in a moving fluid. Sound waves in a flowing medium propagate exactly as light propagates in a curved spacetime. The mathematics maps one onto the other line for line, and a fluid that flows faster than its own speed of sound forms, for the sound trapped inside it, a genuine horizon, a surface of no acoustic return, a sonic black hole. The program born from that observation is called analog gravity, and it has spent 4 decades building horizon physics on laboratory benches, in flowing water, in superfluid helium, in clouds of ultra-cold atoms, each system a translation of untouchable space-time physics into a dialect some instrument can actually read. The rules of evidence in analog gravity are subtle, and the file states them because they govern how much the Chicago result is allowed to prove. An analog system shares the equations of the original, not the substance, so it can confirm that the mathematics does what theorists claim the mathematics does, that the predicted statistics really follow from the predicted transformations, with no hidden inconsistency and no forgotten term. What it cannot confirm is that the real vacuum of spacetime actually undergoes those transformations when a real detector accelerates. The distinction sounds pedantic until you notice that the Belinski school's entire objection lives in exactly that gap. The critics do not claim the Bogoliubov algebra is executed incorrectly, they claim it is executed on the wrong problem, and an analog experiment, executing the same algebra in cesium atoms, cannot referee that dispute. Both camps predicted the condensate would glow. What the analogs demolish is a different and older kind of doubt, the suspicion that the thermal predictions were mathematical mirages that no physical system of any kind would honor. 60,000 atoms honored them, at 2 microkelvin, on camera. The equations, whatever they describe something buildable, and after 2019 the argument is no longer about whether Unruh's mathematics works, it is only about what it is the mathematics of. Parallel to the brute force campaigns, a quieter school of experimental design has spent the last 15 years asking a subtler question. If the bath is too faint to feel as heat, does the vacuum offer any other handle, any property of an accelerated system that accumulates evidence of the warmth without requiring the warmth to trip a thermometer? 3 proposals define this school, and each one attacks the impossible number, the 25 billion grams, from a different flank. The first attacks it with geometry of a purely quantum kind. In 2011, Eduardo Martin Martinez, Yvette Fuentes, and Robert Mann published a proposal in Physical Review Letters, Volume 107, Article 131301, built on a property called the Berry phase. When a quantum system is steered slowly around a closed loop in its space of configurations and returns to where it began, its state comes back multiplied by a phase, a rotation in the abstract space of quantum amplitudes that depends only on the geometry of the loop traversed. The phase is memory without energy, a record of the journey imprinted on the system's wave function. The insight of the 2011 paper is that an atom coupled to a quantum field acquires a Berry phase that depends on whether its vacuum is the cold inertial one or the warm accelerated one, because the Unruh bath deforms the loop the atom's state traces. The deformation is minuscule, but phases have a virtue temperatures lack, they accumulate, and interferometry, the art of comparing phases between 2 paths, is among the most sensitive techniques in all of measurement. The authors calculated that an atom interferometer could resolve the Unruh contribution to the Berry phase at proper accelerations around 10 to the 17 meters per second squared, sustained for times on the order of nanoseconds. That is still a savage acceleration by human standards, 10 million billion Gs, but it sits fully 9 orders of magnitude below the direct detection threshold, a billion times closer to reach, because the experiment no longer asks to feel the heat, only to read the signature the heat's possibility engraves on quantum memory. The second flank is confinement. In 2020, Kinjalk Lochen, Hendrik Ulbricht, Andrea Vinante and Sandeep Goyal, publishing in Physical Review Letters, Volume 125, Article 241301, analysed what happens when the accelerated detector is an atom inside a high-quality optical cavity, a resonator whose mirrors reshape the vacuum between them, concentrating the field's spectral weight into narrow lines. A cavity is a vacuum amplifier in exactly the sense this hunt needs. The Unruh response of a free space detector is spread thinly across all frequencies, while a cavity funnels the relevant fluctuations into resonances where the detector's response is enhanced by orders of magnitude, and a follow-up optimization by Jerome Stargan and Lochen in 2022, in the same journal, Volume 129, Article 111303, sharpened the scheme further. The projected effect remains unobserved, but the arithmetic of these papers moved the required accelerations down into ranges that laser-driven electrons already achieve transiently, converting the question from whether the acceleration can exist to whether it can coexist with the fragile coherence a cavity measurement demands. The trade is characteristic of the entire modern program. Nature will sell the acceleration or the cleanliness, and every design is a negotiation over the exchange rate. The third flank is the strangest, because it proposes that the detection already happens constantly, in every radio antenna on Earth, and that what is missing is not the phenomenon but the bookkeeping. In 2017, Gabriel Cazella, André Landulfo, George Matsas and Daniel Vanzella, the São Paulo School again, published in Physical Review Letters, Volume 118, Article 161102, a proposal with a deliberately provocative architecture. Take the zero-energy Rindler photon accounting this file walked through, the theorem that every ordinary photon radiated by an accelerated charge is, in the accelerated frame, an exchange with the Unruh bath. The transverse momentum distribution of the emitted photons, a quantity classical antenna theory computes and laboratories routinely measure, matches the accelerated frame calculation only when the bath in that calculation sits at exactly the Unruh temperature. Feed the bath any other temperature, including 0, and the distributions disagree. Classical Lama radiation, on this reading, is not merely consistent with the Unruh effect, it is a continuous measurement of the bath's temperature, performed by every accelerated charge in the universe. The authors proposed a concrete implementation, electrons injected at 3.5 megaelectronvolts into crossed fields, an electric field near 1 megavolt per meter and a magnetic field near 1/10 of a Tesla, radius of order 10 centimeters, about 4 inches, bunches of 10 million electrons lasting under a picosecond, reaching proper accelerations around 10 to the 17 meters per second squared, and they closed with a sentence that scandalized and delighted the community in equal measure. Unless one challenges classical electrodynamics, they wrote, our results must be virtually considered as an observation of the Unruh effect. There is a mathematical detail inside that paper worth lifting into the light, because it explains how a quantum temperature can hide inside classical physics at all. The Unruh temperature is proportional to the reduced Planck constant, h bar, the signature of quantum mechanics, and yet the radiation formulas being compared are classical, no h bar anywhere. The resolution is that in the thermal occupation factor governing the exchange with the bath, the h bar in the temperature and the h bar in the photon's energy cancel, leaving an expression classical electrodynamics can verify without ever knowing quantum mechanics exists. The quantum constant enters twice and exits, like a courier who delivers the message and leaves no name. Whether one accepts the conclusion, and many specialists file it under consistency check rather than observation, the structure is a lesson in how deeply the Unruh bath is woven into physics that predates it by a century. Lama published his formula in 1897. On the Sao Paulo reading, he had been computing thermal exchange with the vacuum for 80 years before anyone knew there was a temperature in the room. Set the three flanks side by side and notice what has happened to the shape of the hunt. The direct question, does an accelerated thermometer warm up, remains untouchable, its 25 billion G standing exactly where Unruh left it in 1976. Around it, the field has constructed an envelope of adjacent questions. Does the phase remember? Does the cavity amplify? Does the antenna already testify? Each answerable at accelerations millions to billions of times smaller, each yielding a verdict logically tied to the bath's existence. This is how physics behaves when it cannot storm a result frontally, it besieges, and the siege has a scoreboard. Every adjacent question answered so far, in every medium, has come back on Unruh's side. Nothing has come back against. The absence matters as much as the presence. 50 years of increasingly clever instruments have failed to produce a single anomaly suggesting the vacuum is colder than the formula says it should be. And in experimental physics, a hypothesis that survives every flanking attack while its critics predict it should fail somewhere is accumulating exactly the kind of record that eventually gets called confirmed. Eventually is not yet. The trajectory has a direction though, and before this file weighs the final verdict, the evidence has one more wing. The one where the Unruh bath stops being a target of measurement and becomes a tool that reshapes what measurement itself can do. In the young discipline that studies what acceleration does to quantum information. The discipline is called relativistic quantum information, and its founding observation is one this file has already used without naming it. The vacuum is entangled. The correlations stitched through empty space are not metaphor, they are quantifiable resources. The same entanglement that quantum computers spend and quantum cryptographers guard, present in the ground state of every quantum field, everywhere, for free. In 2003, Benny Resnick demonstrated the consequence that made the field take notice. Two detectors, two simple atoms, switched on briefly at separate locations in the vacuum, can end their interaction entangled with each other, even if the regions where they operated were separated so widely that no signal could travel between them in the time available. The atoms did not create the correlation, they could not have, causality forbids it. They withdrew it. The entanglement was already present in the vacuum between the regions, and the detectors siphoned some into themselves, a process now called entanglement harvesting, a term coined by Nicholas Mennecucci and collaborators around 2012. Empty space, in the operational language of this young field, is a warehouse of pre-positioned quantum correlation, and nothing, harvested correctly, is a resource. Acceleration walks into this warehouse and starts breaking things, which is exactly why it interests us. The Unruh bath, whatever one's philosophical stance on its reality, enters the equations of relativistic quantum information as noise, thermal randomness that degrades the delicate correlations a harvesting protocol tries to extract, and the degradation is calculable, specific, and in principle measurable, which makes it yet another flanking observable for the effect itself. The founding calculation belongs to Yvette Fuentes Schuller and Robert Mann, in a 2005 Physical Review Letters paper, Volume 95, Article 120404, with a title rare for the journal, Alice Falls into a Black Hole. Take two observers sharing a maximally entangled pair of field modes, the standard currency of quantum information. Let one observer, Alice, remain inertial, and let the other, the conventionally named Rob, undergo uniform acceleration. Recompute the entanglement they share from Rob's accelerated perspective, and it is smaller. The Unruh bath in Rob's frame scrambles his half of the correlation, and the degradation worsens as the acceleration grows, entanglement bleeding away towards zero in the limit of infinite acceleration. Correlation, the resource, turns out to be observer-dependent in exactly the way particle content and temperature already were. What Alice and Rob can jointly do with their pair, the codes they can run, the secrets they can share, depends on how Rob moves. Motion taxes information. The 2 decades since have mapped the tax code in detail, and its clauses are stranger than the headline. Greg Salton, Robert Mann, and Nicholas Menicucci showed in 2015 in the New Journal of Physics, Volume 17, that 2 detectors accelerating in opposite directions, back-to-back, can, under the right conditions, harvest more entanglement than inertial detectors, the geometry of their twin horizons restructuring the vacuum correlations they mine. Parallel accelerated detectors, by contrast, lose harvesting power in a pattern with an eerie twin. The calculation matches that of 2 static detectors in a de Sitter universe, an expanding cosmos with a cosmological horizon. One more entry in the ledger of acceleration impersonating gravity that this file opened with the Hawking bridge. A 2022 study by Zhihong Liu, Jialin Zhang, Robert Mann, and Hongwei Yu in Physical Review D, Volume 105, asked the blunt question in its title, "Does acceleration assist entanglement harvesting?" and returned the physicist's favorite answer, "It depends. Enhancement in some regimes of detector separation and switching, degradation in others. The vacuum's generosity a function of exactly how you shake the instruments you dip into it." The newest line, published across 2025 and 2026 in the Journal of High Energy Physics, turns decoherence itself, the fading of quantum superpositions, into the thermometer. A detector prepared in a delicate superposition and accelerated through the vacuum loses its quantum character at a rate the theory now predicts with a universal scaling law, the long-time decoherence rate growing as acceleration raised to the power of 2 delta minus 1, where delta is a number characterizing which property of the field the detector couples to. The formula's promise is practical. Choose a coupling with larger delta, and the acceleration's fingerprint on the fading grows steeper, a more sensitive probe assembled not from better hardware, but from better bookkeeping. Whether these information-theoretic signatures reach the laboratory before the thermal ones is an open race, and it is characteristic of this subject that the race course itself, the mathematics of what acceleration does to knowledge, was terra incognita 25 years ago, and is now a mapped discipline with textbooks. Before I continue into the final part of this file, pause and take stock of what the evidence has assembled, because the inventory is about to be contested, and you should hold it in your own hands first. A formula from 1976, tying temperature to acceleration through the constants of nature. A rigorous theorem certifying the accelerated vacuum as thermal in the strictest mathematical sense. A consistency proof showing quantum field theory contradicts itself between reference frames unless the bath is real, with the accelerated proton's lifetime as the star witness. A resolution of the century-old radiating charge paradox that works only with the bath's participation. A storage ring polarization ceiling of 92.4%, measured, consistent with circular vacuum warmth. A crystal experiment whose published reinterpretation claims the Unruh temperature outright. An ultra-cold atomic cloud in Chicago that executed the mathematics and glowed at 2 microkelvin, excellently agreeing in its author's words with the prediction. On top of it all sits a discipline's worth of information-theoretic corollaries, every one pointing the same direction. That is the case for. It is formidable, layered, and entirely without a direct detection at its center. Now comes the case against, and it does not come from cranks or contrarians on the margin. It comes from serious mathematical physicists publishing in the same journals, and their argument attacks the one place this entire file has treated as bedrock, the mathematics itself. To weigh the objection properly, the file must first display the machinery being objected to, at one level deeper than the curtain and tapestry picture. The derivation every textbook presents runs through 3 moves, each of which the critics will, in turn, place under a microscope. Move 1 is coordinates. The uniformly accelerated observer's experience of spacetime is captured by the Rindler metric, which can be spoken in one breath. The line element ds² equals e to the 2a xi, times the quantity minus d tau squared plus d psi squared, plus the flat transverse directions. Here tau is the accelerated observer's own time, and psi the distance measured along the direction of acceleration. The exponential factor out front is the fingerprint of the frame. Clocks at different depths in an accelerated frame tick at different rates, exactly as clocks at different heights in a gravitational field do, the equivalence principle written as arithmetic. Within these coordinates, the accelerating observer is at rest, and the coordinates cover only the Rindler wedge, the quarter of spacetime this file fenced off hours ago. The metric is not controversial. It is a change of variables, no more exotic than describing a city in polar coordinates centered on your own house. Move 2 is quantization, and here the fork appears. To do quantum field theory, you expand the field in modes and declare which modes count as positive frequency, the declaration that defines particles and the vacuum. The inertial physicist makes the declaration using ordinary Minkowski time. The Rindler physicist makes it using tau, the accelerated time, obtaining a different mode basis and with it the Fulling vacuum, the state an accelerated observer would certify as empty. Fulling's 1973 theorem says these two constructions are inequivalent, and the bridge between them is the pair of Bogoliubov coefficients, alpha and beta, the overlap integrals that express each Rindler mode as a mixture of inertial modes. The beta coefficient is the entire story. If beta vanishes, the two observers agree on what a particle is. It does not vanish. For frequency omega, the squared magnitude of beta comes out as 1 over the quantity e to the 2 pi omega minus 1, and that expression is not just any function. It is the Planck distribution, the exact statistical formula Max Planck wrote down in 1900 for the radiation inside a hot oven, the founding equation of quantum theory itself, now materializing out of a coordinate transformation with the temperature set by the acceleration. Spoken plainly, the average number of Rindler particles the accelerated observer finds in the inertial vacuum equals 1 over e to the 2 pi c omega over a minus 1, a blackbody census in a state guaranteed empty by the other frame. Move 3 is the trace. The Rindler observer's horizon makes the far wedge inaccessible, so the honest description of physics in the near wedge discards, mathematically traces over, everything behind the curtain, and the residue is the mixed thermal density matrix, this file described as ignorance with a spectrum. 3 moves, coordinates, quantization, trace, and out falls Unruh's temperature with the inevitability of long division. This is the calculation the majority of theoretical physicists regard as settled. Now here is what its most serious critics say is wrong with it, and the file owes them the same care it gave the orthodoxy, because their credentials are not marginal, their papers passed peer review in the same journals, and their argument, if correct, deletes the subject. The principal critics are Vladimir Belinski, a general relativist of formidable reputation, co-author of the celebrated BKL analysis of gravitational singularities, together with Boris Karnikov, Vladimir Muir, and Nikolai Narozhny, later joined by Alexander Fedotov, publishing from 1995 onward, with the sharpest statements in JEP letters in 1997, Volume 65, page 902, and Physical Review D in 2001 and 2004. Belinski's opening position, stated in 1995, was total. The effect, he argued, does not exist, calling both the Unruh and related Hawking derivations artifacts resulting from an inadequate treatment of singularities. The 1997 paper with Karnikov, Muir, and Narozhny closed with a sentence physicists still quote at conferences. It is pointless, they wrote, to talk about an Unruh effect, and the behavior of an accelerated detector in the physical formulation of the problem remains open. Their case has 3 prongs, and each targets one of the 3 moves. The first prong attacks the quantization. To define the Rindler modes at all, the critics observe, the standard construction imposes a boundary condition. The field is required to vanish on the edge of the wedge, at the horizon itself. That requirement looks innocent, a technicality of mathematical hygiene, but its physical content is drastic. A field pinned to zero along the horizon cannot carry correlations across it, so the condition surgically severs the right wedge from the left, converting flat Minkowski spacetime, one connected arena, into two causally and now dynamically disconnected half-universes. Quantizing in the wedge with that condition, the critics argue, is not describing an accelerated observer in ordinary space. It is describing a different spacetime altogether, one with a wall built into it, and the thermal state that emerges is physics of the wall, not physics of acceleration. The Minkowski space of the real world and the doubled wedge space of the calculation are, in their phrase, physically unrelated. The second prong attacks the horizon behavior more intimately. Examine the Rindler mode functions near the horizon, and they oscillate infinitely fast, a logarithmic divergence in phase as the coordinate approaches the edge. The horizon, remember, is not a special place. An inertial observer coasting through it notices nothing. Space-time there is as flat and regular as the middle of your room, and there are no sources, no charges, no matter to justify singular behavior. Yet the wedge quantization plants a mathematical singularity precisely there, on a regular, source-free surface. Standard axioms of quantum field theory, the critics contend, forbid exactly this. Wave functions singular at regular points describe no legitimate physical state, and a derivation that requires them has left the theory it claims to be applying. The thermal bath on this reading is manufactured by the singularity, an artifact in the strict sense, a feature of the description with no counterpart in the described. The third prong is the most concrete, because it meets the orthodoxy on its strongest ground, the detector. Fine, say the critics, discard the wedge formalism entirely, follow Unruh's own more physical route, couple a model detector to the field, and compute its response along an accelerated trajectory using only inertial frame quantities. No Rindler modes anywhere. Narozhny, Fedotov, and collaborators constructed such analyses and reported that with the boundary treatment handled to their standards, the detector's response along the accelerated world line fails to be genuinely thermal, and a related calculation found that the spectrum of created pairs registered by a distant accelerated observer matches the inertial one. No extra thermal population at all. Where the orthodox calculation sees a warm bath, their accounting sees the ordinary excitation any jostled detector suffers, dressed up by an illegitimate limit into the costume of temperature. The three prongs assemble into one thesis. The mathematics that produces the Unruh temperature is real mathematics, correctly executed, of the wrong problem. And 50 years of physics has been reading properties of a fictitious boundary condition as properties of the world. If your instinct is to ask how a dispute this fundamental about the existence of an effect in a theory this thoroughly tested can persist for 3 decades among competent professionals, hold the question. It is the right question, it has an answer, and the answer is the final piece of physics in this file. The dispute persists because both sides agree on every number either side can measure with current instruments, and disagree only about the unmeasured regime the numbers extrapolate into. Nature has declined, so far, to referee, and where nature is silent, mathematics argues with mathematics. The majority's rebuttal, and it is a strong one, comes next. The majority's response begins by conceding the premise and rejecting the conclusion. Yes, the defenders say, a boundary condition that pins the field to zero at the horizon would be illegitimate, would disconnect the wedges, would manufacture spurious physics, and that is precisely why the modern formulation of the Unruh effect does not use one. The critics, in this telling, have demolished a 1970s scaffolding that the building no longer stands on. The load-bearing derivation is the Bisognano-Wichmann theorem, and the theorem's entire architecture is designed to avoid the disputed move. It never quantizes in the wedge. It takes the one global Minkowski vacuum, the full, connected, boundary-free state of the whole spacetime, and asks a question that requires no mode choices at all. How does this single state behave when probed only by measurements confined to the wedge? The KMS thermal answer comes out of the global state's own structure, its analyticity, the way its correlations continue smoothly between real and imaginary time, properties that follow from the axioms of quantum field theory with no boundary condition anywhere in sight. The field does not vanish at the horizon in this formulation. Nothing vanishes there. The horizon matters only as the edge of what the accelerated observer can interrogate, and the thermality is a theorem about restricted access to an unrestricted state. On this reading, the singular mode functions that alarm the critics are artifacts of a bad coordinate choice in an old derivation, scaffolding mistaken for structure, while the theorem stands on foundations the critique never touches. Published assessments from the mainstream go as far as calling the critique largely without merit, even while acknowledging, because it is true, that the exchange ran for years in the field's most respected journals. The second line of defense is the one this file has been building all along, and it does not engage the formalism at all. It points at the consistency results. The accelerated proton's decay lifetime is a frame-invariant fact. Both observers watch the same particle live or die, and the two frames calculations agree only when the accelerated frame includes the bath. The photon count from an accelerated charge is a frame-invariant fact, and the accelerated frame reproduces it only through exchange with a bath at exactly the Unruh temperature. Any other value, including 0, breaks the match. These are not interpretations, they are cross-checks with one free parameter, the bath temperature, and the parameter is not adjustable after the fact. It is fixed by Unruh's formula, and then the books either balance or they do not. The books balance. A skeptic who removes the bath must now explain, mechanism by mechanism, how quantum field theory continues to give the same answers in every frame with the balancing entry deleted. And no published version of the critique has carried that burden through the proton calculation or the Lama reconciliation. The artifact hypothesis, in other words, has never been extended into an alternative bookkeeping that works, and in physics, an objection that cannot be grown into a working alternative eventually stops being an objection and becomes a footnote. And yet the file must be honest about a third position, orthogonal to both camps, that has quietly gathered adherents, because it reframes what the argument is even about. In 2006, Lewis Ford and Robert O'Connell published a paper in Physics Letters A, volume 350, under the title, Is There Unruh Radiation? And their answer cut the question in half. The thermal response of an accelerated detector, they and others in this camp accept, follows from quantum field theory. What does not follow, they argue, is the popular image smuggled in by the word radiation, an accelerated object glowing, showering real photons into the surrounding space that an inertial bystander could collect. The detector warms on this view, but does not necessarily broadcast. The bath is real as an experience of the accelerated system and misdescribed as an emission from it. And companion work under the title, The Demise of Unruh Radiation, pressed the distinction further. The camp matters because it exposes how much of the dispute is a fight over which precise sentence the mathematics licenses. Response versus radiation, experienced temperature versus emitted glow, an effect on the mover versus a signal to the watcher. The equations are not in doubt anywhere in this triangle. The words are, and physics, at its foundations, turns out to be startlingly vulnerable to its own vocabulary. Which brings the file to the sentence it has owed you since the opening, the plain statement of where this subject actually stands. And for that, there is no better witness than an experimentalist with skin in the game. Sebastian Oehner, a fellow at the Atomic Institute in Vienna, working on exactly the analog systems this file toured, put it without decoration in December of 2020. To observe the Unruh effect directly, as William Unruh described it, is completely impossible for us today, he said. You would need a measuring device accelerated to almost the speed of light within a microsecond to see even a tiny Unruh effect. and we cannot do that. Set that against the Sao Paulo School's declaration that the effect is mandatory for the consistency of quantum field theory, with no question about its existence, and against Belinski's standing verdict that there is no effect at all, and you have the full, strange truth of the situation laid out in three professional voices. Impossible to see directly, impossible within the standard theory to remove, contested all the while by a serious minority at the root. Hold all three voices at once and notice the precise shape of the gap between them, because it is narrower and stranger than a first hearing suggests. Nobody in this argument disputes a single completed measurement. The polarization ceilings, the channeling spectra, the condensate images, every recorded number is common ground. The dispute lives entirely in the extrapolation, in what quantum field theory commits us to believing about a regime no instrument has entered. And it divides physicists according to something almost temperamental, the weight each is willing to place on consistency as a substitute for contact. One camp says a theory tested to 12 decimal places has earned the right to be believed about its own thermodynamics. Another says the history of physics is a graveyard of extrapolations exactly this confident. Both are describing the same discipline. The question the Unruh effect finally poses is not about acceleration at all. It is about how far a chain of flawless inference can be trusted to carry you past the last thing you can check. And that question, unlike the temperature of the vacuum, is one every field of human knowledge has to answer for itself. There remains one practical matter the defenders and critics agree deserves an answer, and it closes the experimental case. Suppose the direct experiment was someday attempted, a detector at fantastic acceleration in the real, warm universe. The real universe comes pre-filled with the cosmic microwave background, and a fast-moving detector plows through that relic radiation, Doppler shifting it, blue in front, red behind. Could an experimenter even distinguish genuine Unruh warmth from ordinary relic photons rammed into the detector by its own motion? The theory says yes, by symmetry. The Unruh bath, born of the detector's own horizon, is isotropic in the detector's instantaneous rest frame, the same faint temperature in every direction, while Doppler-boosted background radiation carries an unmistakable directional signature, a dipole, hotter along the direction of motion by a factor the formulas fix exactly. One glow wears the observer's motion on its face. The other, eerily, does not, because it is not coming from anywhere. Recent analyses have even mapped how the two signatures interleave for detectors that are both fast and accelerating, and analog tests of the discrimination are being designed in superfluid helium. The experiment remains out of reach. The protocol for believing it when it comes is already written, which is its own quiet measure of how seriously physics takes the warmth of the void. The discrimination problem has one worked example with numbers attached, and the numbers land on the encouraging side, which is rare enough in this subject to deserve its own paragraph. Return to the storage ring regime. Electrons at LEP class energies, centripetal acceleration 2.9 times 10 to the 23 meters per second squared, naive circular Unruh temperature near 1200 Kelvin. Those electrons do not circulate in an idealized void. They circulate in a laboratory on Earth, a 300 Kelvin environment humming with real thermal photons. And the obvious fear is that the ambient warmth of the machine hall swamps whatever the vacuum contributes. Costa and Matsas ran exactly this comparison in their 1995 analysis, computing the accelerated detector's response to the genuine room temperature bath alongside its response to the vacuum, and the time dilation decoupling this file described earlier decided the contest by a landslide. For the ultra-relativistic electron, the 300 Kelvin laboratory's contribution comes out roughly 3 orders of magnitude below the vacuum zone, a 1,000-fold suppression of the mundane explanation, purchased entirely by the electron's speed. The room shouts, and the electron, running at a Lorentz crawl through the room's slow photons, barely hears it, while the acceleration-borne signal, indifferent to velocity, comes through undiminished. The mechanism generalizes. The faster the probe, the deafer it grows to every bath it merely moves through, and the only warmth that survives the deafness is the warmth that rides with the acceleration itself. Nature, which set the threshold so brutally high, also arranged that any probe extreme enough to reach them arrives automatically insulated from the ordinary heat of the world, and an experimental program that looked hopeless on the first pass keeps, on the second pass, finding the door propped open exactly one crack. There is a final horizon to visit, and unlike the others, you are inside it right now. This file has treated horizons as things that happen to other observers, to rockets under impossible thrust, to particles channeled through crystals, to observers hovering over collapsed stars. In 1977, though, Gary Gibbons and Stephen Hawking extended the horizon temperature logic to a third geometry, the one called de Sitter space, the space-time of a universe whose expansion accelerates. In such a universe, every observer is surrounded by a cosmological horizon, a spherical boundary beyond which the expansion carries galaxies away faster than their light can close the gap. Nothing beyond that boundary can ever signal you again. It is the Rindler curtain turned inside out, wrapped around each observer as a sphere, drawn not by the observer's engines, but by the behavior of space itself, and by the now familiar law, where causality draws a curtain, thermodynamics collects a fee. The Gibbons-Hawking calculation attaches to that horizon a temperature. Here is why that stopped being an academic exercise. Since 1998, cosmology has known that the expansion of our own universe is accelerating, driven by whatever we are labeling with the words dark energy. And an accelerating expansion is precisely the condition that builds a cosmological horizon. You have one. It sits at a staggering but finite distance. It hides from you, permanently, everything beyond it, more of reality falling behind it as the acceleration continues. And by the Gibbons-Hawking result, it carries a temperature, fainter by far than any figure in this file, colder even than the black hole whispers we computed, but not zero. The universe you actually live in, at the largest scale anyone can define, is bounded for you by a warm curtain. Not warm enough to feel, not warm enough to measure with any instrument in prospect, but warm as a matter of the same bookkeeping that balanced the accelerated protons' accounts. The emptiness at the end of every sightline has a temperature, and the reason is the same reason a hard accelerating thermometer glows. Some of the tapestry is behind the curtain, and what remains carries the statistics of what was lost. Sit with how the three horizons rhyme, because the rhyme is the deepest single fact this investigation has surfaced. The Rindler horizon, personal, conjured by acceleration, erasable by easing off the throttle. The black hole horizon, local, carved by collapsed matter, escapable by simply staying away. The cosmological horizon, universal, woven by expansion, escapable by nothing. Three curtains with three different causes, and one formula for the warmth of all three. Temperature equals h bar times the horizon's pull, over 2 pi CKB. Physics has a name for a pattern like that, a law showing up in settings that share no mechanism, only a structure. It usually means the law is not about the mechanisms at all. It is about the structure, and the structure here is information, what an observer can and cannot reach. The lesson the Unruh effect began, temperature is a property of access, scales without modification from a laboratory thought experiment to the boundary of the observable universe. Whatever heat fundamentally is, the last 50 years of theory have relocated it, out of substance, out of motion, into the geometry of knowledge itself. Let the file be careful here, in both directions, because a claim that large attracts both cheap wonder and cheap dismissal. Nothing in this rhyme is mysticism. Every step from the 1973 Fulling paper to the entanglement decoherent scaling laws of 2026 is calculation. Published, checkable, disputed where it is disputed in journals and not in manifestos. Nothing in this rhyme is settled doctrine either. The de Sitter temperature shares the epistemic status of its Unruh sibling, mandated by the mathematics, untouched by any thermometer, and a physicist of the Belinski school would file all three horizons under the same suspicion. The rhyme is real. What the rhyme means, whether horizon thermodynamics is a deep window into the constitution of reality or an elaborate artifact of extending quantum field theory past its warranty, is exactly the open question this file has refused to close by fiat, and it stays open here. Before the closing arguments, one more return to the human scale, the last one, because there is a version of this whole subject that fits inside an ordinary evening. Tonight, in your room, with everything off, you will lie in the dark, and the dark will feel like an absence, the way it has felt to every person on every night in history. The physics assembled across this file says the dark is not an absence, it is a medium, stitched with correlations, holding a census of particles that depends on who asks, wrapped at its farthest edge by a boundary with a temperature, and pierced, everywhere, by a relic glow of 2.725 Kelvin that your eyes cannot see, but any radio dish can. Between the warmth you feel under the blanket, molecules jostling, the old census, and the warmth you will never feel, horizons keeping their books, the same word, temperature, stretches to cover machinery so different that the word itself is the last thing the two pictures share. Language lags the universe. It always has. The thermometer on your wall is not wrong. It is answering a smaller question than you thought you were asking, and it took the better part of a century of physics to find the larger question hiding behind it. The closing phase of an evidence file lists what stands between the case and its verdict, and here the obstacles deserve to be named without cushioning. Because they are not engineering inconveniences, they are walls, and knowing their exact height is the difference between a research program and a wish. The first wall is the acceleration itself, and its height must be stated in the units of what humans can actually build. The requirement, sustained proper acceleration in the range of 10 to the 20 meters per second squared and beyond, has appeared throughout this file, but sustained is the word that does the damage. The strongest accelerations technology produces are transient by nature. A laser field flings an electron for the femtosecond the pulse lasts. A crystal channel grips a particle for the picoseconds of its transit through a millimeter of matter. The thermal character of the Unruh bath, the exact Planck-shaped census, is a property of uniform, unending acceleration, the idealized hyperbola with its perfect horizon. And every real trajectory is a finite, ragged approximation, whose response is smeared by its own beginning and end. Theorists quantify the smearing, and it is manageable, but the principle stands. The clean effect belongs to an eternal motion nothing mortal can execute, and every laboratory test is, by construction, a test of a corrected, complicated cousin. Sebastian Erner's sentence from Vienna was not pessimism. A device accelerated to nearly the speed of light within a microsecond, held coherent enough to read a temperature of billionths of a degree, is not on any technology roadmap. Not from the laser community, not from the accelerator community, not from anyone. Physics does have a history of impossible instruments becoming shelf hardware. The detection of gravitational waves waited a century for its impossibility to expire, and it may be that the Unruh measurement is that kind of impossible rather than the permanent kind. No one alive can honestly promise which. The second wall is the glare. Acceleration strong enough to warm the vacuum is, for any charged system, acceleration strong enough to blaze with classical radiation, the Lama shine that scales with the square of the same quantity the signal scales with linearly at threshold. The hunted whisper and the deafening roar rise together, sourced by the same violence, and every proposal in this file is at bottom a scheme for prying them apart. Chen and Tajima's angular blind spot, the Berry phases accumulating memory, the cavities spectral funnel, the Sao Paulo school's transverse momentum bookkeeping, the isotropy test against the Doppler dipole. Each scheme is clever. None has yet been executed to a detection, and the file notes the pattern without cynicism. Separation schemes are where hard experiments live for decades. The solar neutrino problem sat in that condition for 30 years, and it ended in Nobel Prizes, not embarrassment. The third wall is the one the storage rings taught. Real trajectories curve. Circular acceleration, the only kind machines can sustain, refuses to produce a single clean temperature, its vacuum noise depending on speed and acceleration separately, its thermometer readings varying with which internal transition does the reading. The theoretical bridge between the pristine linear result and the measurable circular one carries correction factors that give skeptics honest room to stand, and closing that gap, deriving the circular case with the same rigor Bisognano and Wichmann gave the linear one, remains unfinished mathematics half a century on. The subject's cleanest theorem and its most practical geometry have never fully met, and until they do, every accelerator-based claim will carry an asterisk. The fourth wall is not physical at all. It is definitional, and this file has watched it operate from every side. What counts as observing the Unruh effect? If the answer is a thermometer on an impossibly accelerated world line, reading h bar a over 2 pi c kb, the effect is unobserved and may remain so beyond every horizon of forecasting. If the answer admits frame consistency arguments, the accelerated proton and the reconciled Lama books already testify, and the effect has been indirectly confirmed for decades. If it admits analog systems, 60,000 cesium atoms in Chicago photographed the predicted statistics at 2 microkelvin in 2019. If it admits reinterpretation of strong field data, a published 2025 analysis of the Na63 crystal spectra claims the temperature outright, contested but standing in the literature. 4 thresholds, 4 verdicts, 1 body of evidence. Where you set the bar decides what you believe has already happened, and the community itself has not agreed on the bar. That is not a scandal. It is what the frontier of a discipline looks like from inside, before the textbooks flatten it into a dated list of discoveries. With that, the file arrives at its summation, with the walls acknowledged and the record assembled, and the summation can be compressed into 3 sentences that every camp in this dispute would, with their own inflections, sign. The mathematics of the effect, from the Bogolyubov census to the Bisognano-Wichmann theorem, is as solid as anything in theoretical physics, and the consistency arguments make its removal cost more theory than almost anyone is willing to pay. The direct measurement is beyond present and foreseeable technology, and every laboratory result so far is an analog, an indirection, or a contested rereading. Meanwhile, the minority who call the whole structure an artifact have kept their objection alive, peer-reviewed, for 30 years without either prevailing or surrendering, because the one arbiter who could settle it, an instrument on the impossible world line, has never reported. Mandatory, unmeasured, and disputed. Hold all 3, because all 3 are true at once, and a mind that can hold them without collapsing into either credulity or dismissal has learned the actual lesson this subject teaches, which is what knowledge looks like when inference runs ahead of contact and has to be trusted or not on its record. Which leaves the verdict, and the file will state its own with the reasoning shown, because a summation that hides its weighing is only an opinion. The decisive exhibits are the consistency proofs, and what makes them decisive is their structure. They are not measurements of the bath. They are demonstrations that frame invariant facts, a particle's death, a photon's arrival, come out identical between frames only if the bath is in the accounting. An artifact does not balance books. A bookkeeping fiction, removed, leaves the accounts it balanced in contradiction, and no critic has rebuilt those accounts without it. On the record as it stands, the reasonable position is that the Unruh effect is real physics, its temperature as much a part of quantum field theory as antimatter was before 1932, awaiting its cloud chamber. The verdict is provisional the way every verdict in empirical science is provisional, and one honest sentence must be appended to it forever until the instrument reports. It has never been felt. The warmth of empty space is, today, a certainty of inference, and inference, however flawless, is a debt the universe has not yet been asked to pay in person. What remains is to understand what kind of universe the evidence has been describing, because the Unruh effect, whatever its experimental fate, has already done permanent work on the concepts physics runs on. And that work is the true cargo of this file. The clearest way to see it is to draw up the ledger, 2 columns, what the last 50 years moved into the observer-dependent column, and what stayed absolute, because the pattern in the ledger is the finding. Begin with the migrations. The particle count of a region of space, the seemingly factual census of how many quanta are present, moved. Fulling's 1973 theorem stripped it of observer independence. The inertial observer's zero is the accelerated observer's warm crowd, and no experiment can crown one census the true one, because each is the complete, correct answer to its own frame's question. Temperature moved with it, the entire subject of this file, from property of a place to property of a world line through a place. Radiation moved in 1980, when Boulware's accounting showed the light of an accelerated charge flowing entirely into territory its co-accelerated observer cannot inspect, so that shining itself became a frame-relative verb. Even the direction of an energy exchange moved, absorption in the rocket's frame unfolding as emission in the laboratories, by Unruh and Wald's 1984 calculation, the same single event wearing opposite thermodynamic costumes in the two descriptions. Entanglement, the quantitative resource of the information age, moved in 2005 with Alice and the accelerated Rob, correlation itself thinning under acceleration, knowledge degrading with motion. Particle, temperature, radiation, energy flow, correlation. Column 1 holds most of what a 19th century physicist would have called the furniture of objective reality. Now the second column, and read it carefully, because it is the column that keeps this subject from dissolving into relativism. What stayed absolute is everything that happens, whether the proton decayed, whether the detector clicked, how many photons arrived at the far instrument, and with what distribution of transverse momentum, whether the two atoms ended their protocol entangled. Every frame, inertial or accelerated, agrees on every entry in this column, always, without exception, and the entire machinery of quantum field theory, baths and horizons included, exists precisely to enforce that agreement. The Unruh bath is not a license for observers to inhabit private universes. It is the exact opposite, the correction term that forces all the private descriptions to converge on one public record of events. The descriptions bend so the facts do not. That is the deal the universe turns out to run on. Radical freedom in the telling, iron agreement in the told, and physics spent a century learning which column each concept belongs to, mostly by guessing wrong first. This is the part I return to most often, and I will name why plainly. Nothing in my daily experience distinguishes the two columns. The warmth of a room, the count of things on a table, the light from a lamp, all of it presents itself with the same flat authority, the same texture of simply being so. The ledger says that authority is alone. Some of those properties are facts of the world, some are facts of my passage through it, and no sense I possess can tell which is which from the inside. It took Bogolyubov coefficients and storage rings and 50 years of argument to sort a single one of them, temperature, into its proper column. What else in the inventory of the obvious is sitting in the wrong column right now, waiting for its own 1976 paper? There is no way to know from the chair. That is not a comfortable thought, and this file has not tried to make it one. It is merely the thought the evidence leaves you with, and it has the strange, cold usefulness of all true accounting. With the ledger drawn, run the case file backward one final time, exhibit by exhibit, in the order the investigation actually assembled it, because a verdict is only as good as a juror's memory of the record. The question at intake was a child's question. What does a thermometer read in a truly empty room? The first finding was that the question was underspecified, temperature being a census of molecular collisions that evaporates with the molecules, leaving only the quantum vacuum, the lowest state of inextinguishable fields, stitched through with correlations and wrapped, for any real observer, in the 2.725 Kelvin relic glow of the cosmic microwave background. The second finding was the trio of papers, Fulling in 1973 on the non-uniqueness of the vacuum, Davies in 1975 on the thermal spectra of Rindler and Schwarzschild geometries, and Unruh in 1976 with the detector that clicks, converging on one formula: temperature equals h bar a over 2 pi c kb. Warmth proportional to acceleration through the constants of quantum mechanics, relativity, and thermodynamics. The third finding was the wall in the numbers, 4 times 10 to the minus 21 Kelvin per meter per second squared. 1 full Kelvin costing 2.5 times 10 to the 20 meters per second squared, 25 billion G, with the usable corridor topping out at the Schwinger limit near 10 to the 29 meters per second squared, where the vacuum itself ruptures into electron-positron pairs. The fourth finding was the mechanism, the Rindler horizon. The causal curtain acceleration draws across half of spacetime, and behind the arithmetic, the vacuum's entanglement, so that the accelerated observer's warmth is the statistical shadow of correlations amputated by the curtain, ignorance with a Planck spectrum, and the Bisognano-Wichmann theorem certifying that shadow as exact thermal equilibrium in the strictest KMS sense the discipline owns. The fifth finding was the bridge to gravity, Hawking's 1974 result that black holes radiate at h bar kappa over 2 pi c kb, the same formula wearing surface gravity in place of acceleration, the near-horizon geometry of a black hole flattening into Rindlers, the hovering observer's redshifted Unruh warmth reproducing Hawking's temperature exactly, and the family completed by Gibbons and Hawking's cosmological horizon, 3 curtains, 1 law. Inside that finding sat the quiet astronomical fact: a solar mass black hole radiating at 62 billionths of a Kelvin, 44 million times colder than the microwave sky it hangs in. Every stellar black hole in the present universe therefore absorbing more than it emits, growing, waiting out an evaporation scheduled beyond every meaningful horizon of time. The sixth finding was the consistency core, the reason the majority treats the bath as non-negotiable. The accelerated charge whose larmor shine, all of it, flows beyond the rider's horizon, its books balanced in the rider's frame only by trade in zero-energy Rindler photons with the warm vacuum. The reconciliation completed from Higuchi, Matsus and Sudarsky in 1992 through Landulfo, Fulling and Matsus in 2019. The accelerated proton, forbidden to decay in its own cold frame, decaying anyway in the inertial calculation, the contradiction dissolved only when the co-accelerated frame's Unruh bath pays the energy bill, the 2 lifetimes then agreeing exactly, and Vanzella and Matsus concluding in 2001 that the effect is mandatory for the consistency of quantum field theory itself. Theory's testimony ends there, and it ends unambiguous. Remove the warmth, and quantum field theory purges itself between frames. What the laboratories then made of that testimony, the rings and lasers and crystals and condensates, and what the dissenters made of the mathematics beneath it, the file has heard in full and can now close. Before the last return to the room, the file sets one exercise, because a verdict absorbed passively is not owned. You have now heard the full record, and the productive question is not which camp sounds more confident. Confidence is cheap on every side of this dispute. The productive question is what evidence would move each camp, because a position that nothing could move is not a scientific position. and by that test, all three camps in this argument pass, which is exactly what makes the standoff durable. Ask the majority what would shake them, and the answer is concrete: a clean, null result where the theory demands a signal, a storage ring polarizing past the Sokolov-Ternov ceiling, an accelerated frame calculation of the proton lifetime balancing its books without the bath, a channeling spectrum that refuses the thermal fit under conditions where the fit is mandatory. None has occurred. Ask the critics what would move them, and the answer is equally concrete: a direct detection under conditions their boundary condition objection cannot reach, or the replication and hardening of the Na63 thermal analysis by independent groups with independent systematics. Neither has occurred. Ask the middle camp, the response without radiation school, what would settle their distinction, and they can name the experiment too: a measurement that catches an accelerated detector warming while the surrounding field carries away no compensating quanta, or the reverse. It has never been performed. 3 falsifiable positions, 0 decisive falsifications, 1 wall of acceleration standing between the argument and its referee. Now weigh it yourself, with your own threshold from earlier in this file in hand. If your standard was consistency, the case closed in 2001 with the proton. If your standard was execution of the mathematics in a real physical system, it closed in Chicago in 2019. If your standard was a thermometer on the impossible world line, it remains open, and may outlive everyone who has ever discussed it, including you, including this channel. All 3 standards are defensible. The universe does not tell you which to hold. It only guarantees that whichever you choose, you now hold it knowing exactly what it commits you to, which is more than most certainties in a human life can say. The laboratory record, retold as one motion, is the story of a wall being approached from every direction at once and never quite touched. Bell and Linus read the storage rings, where centripetal accelerations near 3 times 10 to the 23 meters per second squared imply vacuum temperatures around 1200 Kelvin, and found the electron's refusal to polarize past 92.4%, the Sokolov-Ternov ceiling confirmed at Spear, consistent with spins agitated by circular vacuum warmth, an interpretation forever complicated by circular motion's lack of a single clean temperature. Chen and Tajima aimed the Petawatt lasers, computing the vacuum's thermal fingerprint from its autocorrelation function and locating the angular blind spot where the Unruh whisper might outshine the Lama roar, and the extreme light infrastructure now stands across 3 countries with 10 petawatt beams and Unruh physics printed in its scientific case, commissioned, aimed, and so far silent. The Na63 collaboration channeled electrons through aligned crystals at rest frame fields beyond the Schwinger limit, accelerations 10,000 times the 1 Kelvin threshold, and Morgan Lynch's published rereading of their spectra claims the recoil Unruh temperature saturating the data above 22 giga-electron volts, an observation of a Rindler horizon on paper, in Physical Review D, awaiting the replication that decides whether it enters the textbooks or the footnotes. In Chicago, meanwhile, Cheng Qin's group built the mathematics into 60,000 cesium atoms and watched thermal fluctuations bloom from a quantum ground state at 2 microkelvin, excellently agreeing, in the author's words, with Unruh's prediction, an execution of the equations in borrowed matter, exactly as close to the real vacuum as an analog can be and no closer. Around the wall, the flanking instruments accumulate, the Berry phase that would remember the bath at a billionth of the direct threshold, the cavities that funnel the vacuum's fluctuations into readable lines, the Sao Paulo argument that every antenna on Earth has been measuring the bath's temperature since Lama wrote his formula, the entanglement protocols where acceleration taxes correlation on a published schedule, the decoherence laws scaling as acceleration to the power 2 delta minus 1. Beneath it all runs the dispute that will not close, Belinski, Narozhny and Fedotov maintaining in the permanent record that the boundary conditions manufacture the bath, the majority answering through Bisognano and Wichmann that the theorem never needed the boundary. Ford and O'Connell splitting the difference by accepting the warmth and denying the glow, and Sebastian Erne, closest of all of them to an actual apparatus, stating the ground truth of the whole field, that the direct observation is completely impossible for us today. This is what the file found: a temperature required by the self-consistency of the most tested theory in science, approached by half a century of instruments, touched by none of them, and denied by a serious few. The question at intake has its answer, and the answer has a shape no one ordered. Empty space has a temperature. It has never once been felt. Both of those facts are load-bearing. Return then one last time to the room. It is late, or it will be. The house has gone quiet, the screen will go dark, and around your bed the air will hold its ordinary number, 20 degrees, 68 Fahrenheit. Molecules drumming their census on your skin, exactly as they did before you knew the census was the smaller answer. Beyond the walls, the relic glow of the early universe pours through at 2.725 Kelvin, through the roof, through you, on its way to nowhere in particular. Beyond that, the black holes hang colder than the sky they are dissolving into, keeping their 62 billionths of a degree accounts on a schedule that makes the age of the universe a rounding error. Past every sightline, the cosmological horizon closes its sphere around your position, yours, drawn for the world line you happen to ride, warm by a margin no instrument will ever read, hiding its share of the tapestry the way the Rindler curtain hides its share from everything that dares to accelerate. The dark between the stars was never an absence. It is a ledger, balanced to the last zero-energy photon, and the stillness you fall asleep inside is one entry in it, the entry belonging to an observer who moves gently, and so is owed almost nothing. The Unruh effect is the discovery that almost is not nothing. Move differently, and the void owes you heat. The quantum vacuum, the same vacuum in your room tonight, holds a temperature for every possible journey through it, a private warmth for every world line, written in the one formula, h bar a over 2 pi ckb, that ties your motion to the void's glow through every constant nature has. 50 years of physics could not make the vacuum pay out where anyone could watch, and could not make the debt disappear either. And there is a real possibility that the first direct reading belongs to a century that has not started yet, taken by an instrument no one alive will design, confirming or overturning a prediction made by people long past caring. That is not a failure of the enterprise. That is the enterprise, operating at its honest limit, keeping books on regimes it cannot visit, and trusting the arithmetic because the arithmetic has never once betrayed it where it could be checked. Temperature was never a property of the room. It was a property of the journey, and the room only ever seemed warm or cold because you and it were traveling together. That is the finding. It does not need to comfort you. It places you, one world line among all the possible world lines, moving gently through a vacuum that would glow for you if you asked it violently enough, under a sky whose emptiest reaches run 2.7 degrees above absolute zero, inside a horizon that is yours alone. Small, precisely located, and told the truth. That is what this channel is for, and if these long investigations have earned a place in your nights, subscribing is the simplest way to keep them coming, and it genuinely helps this work continue. The file on the temperature of nothing closes here, unfinished in exactly the way the universe insists on, and it will stay open on the shelf until a thermometer, somewhere, on some impossible journey, finally reports back. Good night.